On July 1st, 2025, astronomers detected something extraordinary racing toward the Sun. Something that didn't belong here. Something from another star system, travelling at speeds that defied everything we thought we knew about cosmic wanderers in our neighbourhood. They named it 3 Atlas, the third confirmed interstellar object ever discovered, and for months it has captivated scientists, sparked fierce debates, and ignited one of the most controversial discussions in modern astronomy. Because while most researchers agree this is simply a comet from beyond our solar system, one prominent voice has been suggesting something far more unsettling. Harvard astrophysicist Avi Loeb has proposed that 3I Atlas might not be what it appears, that its trajectory is too perfect, its timing too convenient, its behaviour too unusual, and that on October 29, 2025, when it disappeared behind the Sun, hidden from every telescope on Earth, it might have done something extraordinary, something intentional. The question that has dominated headlines and social media for weeks is this: is 3I Atlas staying in our solar system? Did it use the Sun's gravity to capture itself into orbit, transforming from a passing visitor into a permanent resident? And if so, why? Tonight, we're going to explore every facet of this cosmic mystery. We'll trace 3I Atlas from its discovery through its hidden perihelion passage, examine the scientific evidence, confront the controversial hypotheses, and ultimately reveal what's actually happening with this interstellar traveller. Because the truth, as it turns out, is both more mundane and more fascinating than the speculation suggests. But first, we need to go back to the beginning, to the moment when humanity first glimpsed this visitor from the void. The Atlas Telescope Network, which stands for Asteroid Terrestrial Impact Last Alert System, was designed with a singular purpose: to protect Earth from potential asteroid impacts by scanning the skies continuously, cataloguing everything that moves through our cosmic neighbourhood. The system consists of multiple telescopes positioned around the globe, each one equipped with ultra-wide-field cameras capable of photographing vast swathes of sky in a single exposure. On any given night, Atlas captures thousands of images, and sophisticated software automatically compares them to previous observations, flagging anything that has moved or changed. The Atlas system represents a remarkable achievement in automated astronomy. Unlike traditional telescopes that focus on small regions of sky in exquisite detail, Atlas sacrifices resolution for coverage. Each telescope can image hundreds of square degrees in a single exposure, equivalent to thousands of full moons placed side by side. The cameras are specially designed with wide-field optics that minimize distortion across these enormous fields of view, while still maintaining enough resolution to detect relatively faint objects down to about magnitude 19 or 20, depending on conditions. The software pipeline that processes Atlas images is equally sophisticated. Every image is automatically calibrated, removing instrumental artifacts and correcting for atmospheric effects. Then it's compared pixel by pixel to reference images taken days, weeks, or months earlier. Anything that has moved, brightened, dimmed, or appeared where nothing existed before gets flagged for human review. On a typical night, this might generate hundreds of candidates requiring verification, most of which turn out to be known asteroids, distant satellites, cosmic rays hitting the detector, or various forms of noise. But on the night of July 1st, 2025, the Atlas telescope in Rio Hurtado, Chile, captured something genuinely unusual. The facility, perched in the foothills of the Andes with clear dark skies and exceptional atmospheric conditions, had been scanning the region around Sagittarius, photographing the dense star fields near the Milky Way's galactic center. At coordinates right ascension, 18 hours, and declination -20 degrees, in a region crowded with thousands of background stars, the automated software detected a faint smudge of light that hadn't been present in previous images. At first glance, it appeared to be just another asteroid or comet, one of millions of small bodies that populate our solar system. The magnitude was approximately 17, bright enough to be detected but not bright enough to be visible to amateur astronomers with typical equipment. The object showed slight elongation, suggesting either motion during the exposure or a diffuse appearance rather than a point-like star. This alone wasn't unusual. Comets often appear fuzzy due to their surrounding coma of gas and dust. But when the on-duty astronomer ran preliminary trajectory calculations using the object's position, and the brief motion detected across multiple exposures that night, something immediately stood out. The object wasn't moving like typical solar system bodies. Its apparent motion across the sky was wrong. Too fast and in the wrong direction for a main belt asteroid, wrong for a Jupiter Trojan, wrong for a trans-Neptunian object. The preliminary orbital elements suggested something extraordinary. When astronomers calculated its trajectory more carefully, incorporating the rate of motion and the direction, they realized something was profoundly different. This object wasn't following a typical elliptical orbit around the Sun. Instead, it was moving on what's called a hyperbolic path, a trajectory that meant only one thing: it had come from somewhere else, from interstellar space. The discovery was announced to the Minor Planet Center on July the 2nd, and within hours, observatories around the world were scrambling to point their telescopes at this cosmic interloper. The Minor Planet Center, operated by the International Astronomical Union, serves as the central clearinghouse for observations of asteroids, comets, and other small solar system bodies. When a potential discovery is reported, the center's staff verify the observations, check against known objects to avoid duplicate discoveries, and if the object appears genuinely new, issue a circular announcing it to the global astronomical community. The announcement of 3I Atlas triggered an immediate response. Observatories across multiple continents began acquiring confirming observations, each one adding to the growing dataset that would allow precise determination of the object's orbit. Within the first 24 hours, more than a dozen separate facilities had reported detections. The Pan-STARRS telescope in Hawaii, the Catalina Sky Survey in Arizona, various European telescopes, and numerous amateur astronomers with capable equipment all contributed data points. But more exciting than the confirmations was what happened next: the hunt for pre-discovery images. Whenever a new object is discovered, astronomers immediately search through archives of previous sky surveys, looking for serendipitous captures of the object before it was officially found. These pre-discovery detections can extend the observational baseline by weeks or months, dramatically improving orbital calculations. For an object like 3I Atlas with unusual orbital characteristics, these earlier observations were crucial. Pre-discovery images were quickly uncovered from archives, extending observations back to June 14th, more than 2 weeks before the official discovery. The Zwicky Transient Facility at Palomar Observatory in California had captured 3I Atlas multiple times between June 14th and 29th, though the automated detection algorithms hadn't flagged it as particularly interesting at the time. Additional Atlas observations from the network's other telescopes were found dating back to early June. These earlier images showed that 3I Atlas had been approaching from the direction of Sagittarius, passing through dense background star fields that had made it difficult to detect until it emerged into clearer regions of sky. Amateur astronomer Sam Dean, who has made a hobby of searching archives for pre-discovery observations of interesting objects, noted additional sightings from as early as June 5th. He also made an astute observation about why 3I Atlas hadn't been discovered earlier. It was passing in front of the galactic center's dense star fields, where the comet would be hard to discern. This illustrates one of the fundamental challenges in detecting interstellar visitors. They can come from any direction, and if their path happens to take them through crowded regions of the sky, where millions of background stars create a confusing backdrop, even relatively bright objects can escape notice. The designation 3I Atlas tells us several important things. The 3I means this is the third confirmed interstellar object, with the I specifically denoting its interstellar origin. The first was Wana, Oumuamua, discovered in October 2017, which sparked intense scientific debate about its unusual cigar-like shape and unexpected acceleration. The object's name comes from the Hawaiian word roughly meaning scout or messenger from afar arriving first, reflecting both its interstellar origin and its discovery by telescopes in Hawaii. The second interstellar object was Tusas E. Borisov, found in August 2019 by amateur astronomer Gennady Borisov, using a telescope he built himself in Crimea. Unlike Oumuamua, which showed no clear signs of cometary activity, Borisov appeared to be a more conventional comet with a clear coma and tail. It provided extensive data over several months of observations, revealing chemical compositions similar to comets in our own solar system despite its extrasolar origin. Now, 3I Atlas joined this exclusive club, but it would prove to be unlike either of its predecessors in several unexpected ways. The Atlas portion of the name credits the Discovery Telescope, following the standard convention of naming comets after their discoverers. In this case, since Atlas is a survey project rather than an individual person, the telescope network itself gets the naming credit. What made astronomers immediately certain of 3I Atlas's interstellar nature wasn't just its trajectory, but its velocity. Understanding why velocity is such a definitive indicator requires delving into some orbital mechanics fundamentals. When an object originates within our solar system, its speed relative to the Sun is constrained by the Sun's gravity. Objects can orbit fast or slow, depending on their distance. Mercury races around the Sun at 47 km per second, while Neptune plods along at just 5 km per second. But there's a maximum speed called escape velocity, and it depends on how far you are from the Sun. At Earth's distance from the Sun, escape velocity is about 42 km per second. That means if you're standing on Earth's orbit and moving faster than 42 km per second relative to the Sun, you'll escape and never come back. Farther from the Sun, escape velocity is lower. At Jupiter's orbit, it's about 18 km per second. Way out in the Oort cloud, thousands of astronomical units distant, escape velocity drops to just meters per second. If something is moving faster than the local escape velocity, it cannot be gravitationally bound to the Sun. It must have come from somewhere else, bringing its kinetic energy from outside our solar system's gravitational influence. This hyperbolic excess velocity, often denoted v infinity, represents the speed the object had when infinitely far from the Sun, before the Sun's gravity began accelerating it inward. 3I Atlas was clocked at approximately 58 km per second relative to the Sun when it entered the solar system. That's more than 130,000 miles per hour, or about 209,000 km per hour. To put this in perspective, that's roughly 200 times faster than a typical commercial jetliner and about 60 times faster than a rifle bullet. At this speed, you could travel from New York to Los Angeles in about 30 seconds, or circle the Earth's equator in less than 4 minutes. As 3 Atlas fell toward the Sun, pulled by gravity, that speed increased, following the precise predictions of Kepler's laws and Newton's gravitational equations. The closer it got to the Sun, the faster it moved, storing gravitational potential energy as kinetic energy. At its closest approach, its perihelion on October 29th, it reached a maximum velocity of about 68 km per second relative to the Sun, or roughly 245,000 km per hour. This is fast enough to cross the entire diameter of Earth in less than a minute. This hyperbolic excess velocity definitively proved 3I Atlas's interstellar origin. Nothing born in our solar system moves that fast unless something catastrophically accelerated it, and there was no evidence of any such event. The velocity was too high to be explained by any known solar system process. No planetary encounter could impart that much speed. No solar eruption or impact event could accelerate a large object to such velocities. The only explanation that fits the data is that 3I Atlas came from another star system, travelling for potentially millions or billions of years through the void between stars. But speed alone wasn't the only remarkable feature. 3I Atlas also had the highest orbital eccentricity ever measured for an interstellar visitor, with a value of approximately 6.15. Eccentricity describes the shape of an orbit, and it's a fundamental parameter in understanding celestial mechanics. A perfect circle has an eccentricity of 0. Every point on the orbit is equidistant from the central body. Earth's slightly elliptical orbit has an eccentricity of just 0.017, meaning it's very nearly circular. Mars has a more elongated orbit with an eccentricity of 0.093, while Mercury's orbit reaches 0.216. Comets with very stretched ellipses, those that spend most of their time in the distant outer solar system and only rarely swing close to the Sun, can have eccentricities approaching, but not quite reaching, Stamno. Halley's Comet, for instance, has an eccentricity of 0.967, meaning its orbit is highly elongated but still closed, still bound by the Sun's gravity. An eccentricity of exactly 1 point or so represents a parabolic orbit, the boundary case between bound and unbound trajectories. Anything with an eccentricity greater than 1.0 is on a hyperbolic escape trajectory. These are open curves, not closed ellipses. They pass by the Sun once and never return. Oumuamua had an eccentricity of 1.2, definitively hyperbolic, but not by a huge margin. Borisov came in at 3.4, clearly unbound with significant excess velocity. But 3i Atlas, with its 6.14 eccentricity, was moving so fast relative to the Sun that its trajectory appeared almost perfectly straight rather than curved. To visualize this, imagine plotting the orbit on a graph. An ellipse with low eccentricity looks like an oval, perhaps slightly stretched but recognizably elliptical. As eccentricity increases toward 1.0, the ellipse becomes more and more elongated, stretching into a cigar shape. At exactly 1.0, it becomes a parabola, a curve that opens infinitely in one direction. Above 1.0, it becomes a hyperbola, and the higher the eccentricity, the more the curve resembles a straight line that bends only slightly as it passes near the Sun. For 3 Atlas, with its extreme eccentricity, the bending is so slight that if you plotted its path through the inner solar system, it would look almost like a straight line aimed at the Sun, making a small deflection as gravity pulls it into a shallow curve, then continuing outward on a slightly different heading. The Sun's immense gravitational field, capable of holding planets in orbit for billions of years, barely perturbs 3i Atlas's trajectory. It's moving simply too fast for the Sun to capture. Early observations from multiple telescopes confirmed that 3i Atlas was actively outgassing, producing a diffuse coma of gas and dust that identified it as a comet rather than an asteroid. This distinction is important because it tells us about the object's composition and thermal evolution. Asteroids are rocky or metallic bodies, essentially inert chunks of rock and metal that formed in the hotter inner regions of protoplanetary disks where temperatures were too high for volatile ices to condense. Comets formed in colder regions where water ice, carbon dioxide ice, carbon monoxide ice, and other volatile compounds could freeze solid and accumulate into icy bodies. When a comet approaches the Sun and begins to warm, these ices sublimate. They transition directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, a tenuous atmosphere surrounding the nucleus and eventually the tail, that iconic streaming feature that makes comets so recognizable. The rate of outgassing depends on temperature, which depends on distance from the Sun, which means comets become more active as they approach perihelion. Images from the Nordic Optical Telescope on July 2 showed 3i Atlas was clearly active, with a fuzzy appearance extending beyond a compact nucleus. This was significant because it meant we'd be able to study the composition of material from another star system as it vaporized under solar heating, potentially revealing clues about the chemical conditions where it formed billions of years ago. Spectroscopy, the technique of splitting light into its component wavelengths to identify which atoms and molecules are present, would be crucial for characterizing 3 Atlas. But there was something unusual about the early observations that would become one of the first hints of the controversies to come. 3 Atlas was remarkably bright for its distance when first discovered. At approximately 4.5 astronomical units from the Sun, well beyond the orbit of Mars, most comets remain frozen and inactive. The region between Mars and Jupiter, around 3 to 5 AU from the Sun, is typically where comets begin showing faint activity, but dramatic comas and tails usually don't develop until comets cross inside Mars's orbit at about 1.5 AU. Yet 3i Atlas was already producing a detectable coma at 4.5 AU, bright enough to be spotted at magnitude 17 despite its great distance. This suggested either a very large nucleus reflecting lots of sunlight, or unusually volatile rich composition that began sublimating at lower temperatures than typical solar system comets, or both. Initial attempts to estimate the size based on brightness yielded surprisingly large values, potentially 15 to 20 kilometers in diameter, if the object were a relatively dark, asteroid-like body. This early brightness would become one of several features that Avi Loeb and others would later cite as anomalous. Why would an interstellar comet begin outgassing so far from the Sun? Was its composition truly different from solar system comets, enriched in supervolatile species that sublimate at very cold temperatures? Or was there another explanation? These questions would percolate through the astronomical community over the following weeks and months. Within the first week of its discovery, 122 observations had been collected from 31 different observatories worldwide. This represented an impressive level of international coordination and scientific interest. astronomers were tracking its position with increasing precision, refining predictions about where it would go and when it would reach key milestones in its journey through the inner solar system. Each new observation added to the data set, improving the orbital solution, narrowing the uncertainties in position and velocity predictions. The rapid accumulation of data was crucial because interstellar objects don't wait around. They're moving fast, typically visible for only a few months before they speed away beyond the reach of most telescopes. Oumuamua had been discovered on its way out of the solar system and remained observable for only about 2 months. By the time astronomers fully appreciated how unusual it was and how valuable additional observations would be, it had already faded beyond detection limits. The astronomical community didn't want to make the same mistake with 3I Atlas. Major observatories immediately began allocating telescope time for 3I Atlas observations. The Hubble Space Telescope, despite its packed schedule of observations years in advance, has mechanisms for inserting time-critical targets. Hubble's ability to image faint objects with exquisite resolution makes it ideal for studying cometary nuclei, potentially resolving the nucleus from the surrounding coma to measure its true size. The James Webb Space Telescope, humanity's most powerful infrared observatory, would be perfect for spectroscopic characterization of the coma's composition. Ground-based observatories with large telescopes and advanced instrumentation also joined the campaign. The Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Gemini telescopes, and numerous other facilities scheduled observations to track 3I Atlas's evolution as it approached the Sun. Amateur astronomers with modest equipment contributed valuable photometric data, measuring the comet's brightness changes over time, which can reveal rotation periods and outburst activity. The scientific community was electrified. Only 3 interstellar objects in all of human history had been definitively identified, and each one offered a unique window into the processes occurring in distant star systems. Oumuamua had been controversial and brief, visible for only a few weeks before speeding away beyond the reach of most telescopes. Borisov had been more cooperative, remaining observable for months and providing extensive data on its composition and behaviour, confirming that at least some interstellar comets are quite similar to our own solar system's comets, despite their exotic origins. Now, 3I Atlas presented a third opportunity, and it was approaching the Sun at a time when humanity's most powerful telescopes, including the James Webb Space Telescope, launched in 2021, and the recently operational Vera Rubin Observatory, were available and ready to study it in unprecedented detail. The timing couldn't be better. We had infrared capabilities Webb provides, ultraviolet capabilities from Hubble, extensive ground-based spectroscopic facilities, and spacecraft throughout the solar system that might catch glimpses of this visitor. Conferences were hastily organized to coordinate observations and share preliminary results. Scientific papers were being drafted even before key data was collected, with researchers reserving journal space to publish findings quickly while the object remained newsworthy. Press releases were prepared, public outreach materials were developed, and social media began buzzing with excitement about this messenger from another star. But even in those early days of discovery, questions were already being raised. Questions about its trajectory, its brightness, its composition. Questions that would evolve over the following months into one of the most contentious debates in modern astronomy. Because while most scientists saw 3 Atlas as an extraordinary but ultimately natural phenomenon, one prominent researcher was beginning to notice things that didn't quite add up. Things that would lead him to propose a hypothesis so controversial it would dominate headlines, trigger intense backlash from colleagues, and force the scientific community to confront uncomfortable questions about how we evaluate extraordinary claims. The stage was set for what would become not just a scientific investigation, but a philosophical debate about the nature of evidence, the boundaries of speculation, and what we should do when the universe presents us with something we don't fully understand. As July progressed into August and September, the coordinated observation campaign for 3I Atlas became one of the most intensive efforts in the history of small-body astronomy. Observatories on 6 continents contributed data, creating a nearly continuous monitoring program that tracked the comet day and night as Earth's rotation brought different facilities into darkness. The diversity of observing techniques employed reveals just how sophisticated modern astronomy has become. Photometry, the precise measurement of an object's brightness over time, can reveal rotation periods if the nucleus is non-spherical or has patches of different reflectivity. For 3i Atlas, photometric observations suggested a rotation period of approximately 16.16 hours, with variations in brightness implying an elongated or irregularly shaped nucleus. Spectroscopy provided chemical fingerprints. When sunlight reflects off a comet's nucleus, or shines through its coma, atoms and molecules absorb specific wavelengths corresponding to their quantum energy levels. By spreading the light into a spectrum and looking for these absorption or emission lines, astronomers can identify what elements and compounds are present. Different observatories use different spectroscopic techniques: low-resolution spectra to identify major constituents, high-resolution spectra to measure precise wavelengths and detect subtle features, and time series spectroscopy to watch how composition evolved as the comet's activity changed. Imaging provided context and structure. While point source photometry tells you how bright something is, resolved imaging shows its shape, extent, and morphology. For 3i Atlas, imaging revealed the developing coma, the nascent tail structure, and eventually the jets of material streaming from the nucleus. Adaptive optics systems on large ground-based telescopes, which use deformable mirrors to compensate for atmospheric turbulence in real time, achieved resolutions comparable to space telescopes for bright targets. Polarimetry measured how light from 3i Atlas was polarized, which provides information about the size, distribution, and composition of dust particles in the coma. Light scattering off dust grains becomes polarized to a degree that depends on the particle's size, shape, and refractive index. These measurements help distinguish between different types of dust, whether silicate minerals, carbonaceous material, or icy grains. Radio observations attempted to detect molecular emission lines in the microwave and millimeter wavelength ranges. Molecules like water, carbon monoxide, hydrogen cyanide, and methanol emit characteristic radio signals that can be detected with radio telescopes. These observations complement optical and infrared spectroscopy, accessing different molecular species and sometimes achieving better sensitivity for specific molecules. The sheer volume of data being generated was staggering. Every night brought dozens of new measurements from multiple facilities. Raw images needed to be calibrated, removing instrumental signatures and atmospheric effects. Spectra needed to be extracted, wavelength calibrated, and analyzed. Orbital positions needed to be measured with sub-arc-second precision, accounting for the comet's motion during exposures and the varying positions of Earth-based observers. This is modern astronomy at its finest. Hundreds of researchers coordinating observations, sharing data through online databases, publishing preliminary results to preprint servers where colleagues can access them immediately rather than waiting months for peer review and journal publication. The pace of discovery has accelerated dramatically in recent decades, enabled by digital communication and communities built around shared scientific interests. Yet despite this unprecedented observational coverage, or perhaps because of it, anomalies and puzzles began emerging. The more we learned about 3i Atlas, the more questions arose. Was its unusual brightness due to size or composition? Why was the CO2 to water ratio so extreme? What caused the peculiar anti-tail structure? Each new measurement seemed to answer old questions while raising new ones, a pattern familiar to anyone who studies complex natural phenomena. And in the background, threading through conference presentations and informal discussions, a more provocative question began circulating. What if we're not looking at a natural object at all? Before we dive deeper into the controversy surrounding 3i Atlas, we need to understand a fundamental concept of orbital mechanics, the difference between bound and unbound trajectories. This distinction is crucial because it determines whether an object will remain in the solar system or escape into interstellar space. And despite what some headlines have suggested, the physics here is crystal clear and has been tested countless times with extraordinary precision. Imagine throwing a baseball straight up into the air. You release it with some velocity, and gravity immediately begins pulling it back down. The ball rises, slowing as gravitational potential energy replaces kinetic energy, until it reaches a maximum height where all its upward velocity has been converted to potential energy. Then it falls back down, accelerating as that potential energy converts back to kinetic. No matter how hard you throw it, unless you can achieve escape velocity, which is about 11 kilometers per second from Earth's surface, that ball will always return to Earth. The escape velocity represents the minimum speed needed to escape Earth's gravitational field and never fall back. The same principle applies to objects orbiting the Sun, but with one critical difference. An object in orbit has both vertical and horizontal motion, creating the elegant elliptical paths we see planets and comets follow. An orbit is essentially perpetual falling, where an object moves sideways fast enough that as it falls toward the central body, the curvature of its fall matches the curvature of the planet or star it's orbiting. It keeps missing, perpetually falling in a circle or ellipse. Every orbit is defined by its energy, which is a combination of kinetic energy from motion and gravitational potential energy from the object's position in the gravitational field. The total energy determines whether the orbit is bound or unbound. If an object's total energy is negative, meaning the attractive gravitational potential energy outweighs the kinetic energy of motion, it will follow an elliptical orbit. It might travel far from the Sun, like comets from the Oort cloud that venture thousands of astronomical units outward, but it will always swing back, trapped forever in the Sun's gravitational embrace. These objects are gravitationally bound to the Sun, permanent residents of our solar system. The mathematics of this is elegant and precise. The total energy E of an orbiting body is given by E sast 1 out 2 mv2 gm mas gr, where m is the mass of the object, v is its velocity, g is the gravitational constant, m is the mass of the Sun, and r is the distance from the Sun. The first term represents kinetic energy, energy of motion, and the second term represents gravitational potential energy, energy of position in the gravitational field. When E is negative, kinetic energy is insufficient to overcome gravitational binding, and the orbit is elliptical and closed. If an object's total energy is exactly zero, it follows a parabolic trajectory, barely escaping with no energy left over. This is the theoretical boundary between bound and unbound states, though in practice, we rarely see perfectly parabolic orbits because they require such precise conditions. An object on a parabolic trajectory will escape to infinity, but arrive there with zero velocity, having spent all its kinetic energy climbing out of the Sun's gravitational well. But if an object's total energy is positive, meaning it has more than enough kinetic energy to escape the Sun's gravity, it follows a hyperbolic trajectory. It will swing past the Sun once, accelerating as gravity pulls it inward, then slowing as it climbs back out of the gravitational well. But unlike elliptical orbits, hyperbolic paths never close. They continue outward forever, asymptotically approaching a straight line as the Sun's influence fades to insignificance. The object will never return. It carries with it excess kinetic energy that it will retain even when infinitely far from the Sun. If an object's total energy is exactly zero, it follows a parabolic trajectory, barely escaping with no energy left over. This is the theoretical boundary between bound and unbound states, though in practice we rarely see perfectly parabolic orbits because they require such precise conditions. But if an object's total energy is positive, meaning it has more than enough kinetic energy to escape the Sun's gravity, it follows a hyperbolic trajectory. It will swing past the Sun once, accelerating as gravity pulls it inward, then slowing as it climbs back out of the gravitational well. But unlike elliptical orbits, hyperbolic paths never close. They continue outward forever, asymptotically approaching a straight line as the Sun's influence fades to insignificance. The object will never return. 3 Atlas is definitively on a hyperbolic trajectory. Its orbital eccentricity of 6.14 places it far into hyperbolic territory, with an enormous excess of kinetic energy over what would be required to merely escape. When astronomers trace its path backward, they can determine that it came from interstellar space, travelling for potentially millions or even billions of years through the void between stars. And when they project its path forward, the math is unambiguous. 3I Atlas will leave the solar system and continue into interstellar space, never to return. The amount of energy required to capture 3I Atlas into a bound orbit around the Sun is staggering. At perihelion, its closest approach to the Sun, 3I Atlas was moving at approximately 68 kilometers per second. To slow it enough to transition from hyperbolic to elliptical would require reducing that velocity by a significant fraction, perhaps 10 to 20 kilometers per second, depending on the desired final orbit. For an object with the estimated mass of 3I Atlas, which recent calculations place at a minimum of 33 billion metric tons, this would require an energy expenditure equivalent to trillions of nuclear weapons. Natural processes don't provide that kind of energy. Outgassing from a comet, where jets of sublimating ice push on the surface like tiny rocket engines, can cause small perturbations to a trajectory. These non-gravitational accelerations are routinely measured on active comets, and they can accumulate over time to produce noticeable changes in position. But they're measured in meters per day squared, not kilometers per second. The thrust from cometary outgassing is simply too weak, spread over too large a surface area, to significantly alter the velocity of a massive object like 3I Atlas. Gravitational interactions with planets could theoretically alter 3I Atlas's trajectory, but the geometry doesn't support it. To capture an object into orbit through gravitational assist, you need to pass extremely close to a massive planet at exactly the right angle and velocity. The closer you pass and the more massive the planet, the more your velocity can change. Jupiter, with its enormous mass, is the master of this technique, having captured numerous comets into orbit around the Sun through close encounters. But 3I Atlas's closest approach to Jupiter will be about 54 million kilometers in March 2026, far too distant for any significant gravitational interaction. Its pass by Mars was closer, about 28 million kilometers, but Mars is simply too small to have any meaningful effect on something moving as fast as 3I Atlas. The orbital mechanics are straightforward and have been calculated by hundreds of astronomers worldwide using observations from more than 200 observatories. The data shows 3I Atlas following a smooth, predictable hyperbolic path that matches gravitational models to within tight margins. There is no evidence of sudden velocity changes, no unexplained accelerations that would indicate a maneuver to slow down, no deviation from the trajectory that natural forces would produce. And yet, one prominent voice in the scientific community has suggested that 3I Atlas might have executed precisely such a maneuver. That during its closest approach to the Sun, when it was hidden from Earth's view behind our star's overwhelming glare, it might have fired engines or employed some advanced propulsion system to brake itself into a bound orbit. This is the reverse Oberth maneuver hypothesis, and understanding it requires us to delve into one of the most controversial figures in modern astronomy and his history of making extraordinary claims about interstellar visitors. Abraham Avi Loeb is not your typical astronomer. As the Frank B. Baird Jr., Professor of Science at Harvard University and former chair of the Astronomy Department, from 2011 to 2020, he has built an impressive career studying some of the most fundamental questions in astrophysics. His early work focused on black holes, exploring how these gravitational monsters grow and influence their surroundings. He made significant contributions to understanding the formation of the first stars in the universe, those primordial stellar furnaces that lit up the cosmic dark ages after the Big Bang. He's published more than 900 scientific papers, mentored dozens of graduate students and postdoctoral researchers, and served on numerous prestigious scientific committees. His credentials are impeccable. He's received awards including the Sackler Prize in Astrophysics, has served on the President's Council of Advisors on Science and Technology, and chaired the board on Physics and Astronomy of the National Academies. He was the founding director of Harvard University's Black Hole Initiative, a research center dedicated to studying these enigmatic objects from multiple disciplinary perspectives. His intellect is formidable, his productivity extraordinary, his contributions to astrophysics substantial and widely recognized within the scientific community. But in recent years, Loeb has become known publicly for something else: his willingness to entertain, advocate for, and sometimes aggressively promote the possibility that some astronomical objects might be artifacts of extraterrestrial technology rather than natural phenomena. This shift began in earnest in 2017 with the discovery of Oumuamua, the first confirmed interstellar object to pass through our solar system. And it's a shift that has made him simultaneously one of the most visible astronomers in the world and one of the most controversial figures in his field. Oumuamua was discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. The name means scout, or first distant messenger in Hawaiian, reflecting both its interstellar origin and the fact that it was discovered by Hawaiian-based telescopes. Initial observations showed it was tumbling through space in a complex rotation, and its brightness variations suggested an extremely elongated shape, perhaps 10 times longer than it was wide, like a cosmic cigar or pancake. But the truly puzzling feature emerged when astronomers measured its trajectory with high precision. Oumuamua wasn't following a purely gravitational path. It was accelerating away from the Sun in a way that gravity alone couldn't explain. The deviation was small but statistically significant, amounting to a few parts in 10,000 in acceleration, but definitely there. For a comet, this would be easily explained. Outgassing produces thrust that accelerates the nucleus. But Oumuamua showed no obvious signs of cometary activity. No coma was detected, no tail, no spectroscopic evidence of gas emission. Various explanations were proposed. Maybe it was outgassing, but the gas was composed of species that don't produce visible optical emission, like molecular nitrogen or hydrogen. Maybe the outgassing was asymmetric, coming predominantly from one side heated by the Sun, making it hard to detect. Maybe it had unusual thermal properties that concentrated sublimation to specific regions. These were all plausible natural explanations requiring only modest assumptions about composition or structure. But in November 2018, Loeb and postdoctoral researcher Shmuel Bialy published a paper in the Astrophysical Journal Letters titled, "Could Solar Radiation Pressure Explain Oumuamua's Peculiar Acceleration?" The paper explored whether solar radiation pressure, the tiny force exerted by sunlight pushing on surfaces, could account for the acceleration if Oumuamua were an extremely thin, lightweight structure. Their calculations showed that if Oumuamua had a thickness of less than a millimeter but a large surface area, radiation pressure would produce exactly the observed acceleration. This was presented as a natural explanation comparable to the other hypotheses, but Loeb went further in the paper's conclusion, writing, "Considering an artificial origin, one possibility is that Oumuamua is a light sail floating in interstellar space as debris from an advanced technological equipment. This would account for the various anomalies of Oumuamua, such as the unusual geometry inferred from its brightness variation, its low thermal emission suggesting high reflectivity, and its deviation from a Keplerian orbit without any sign of a cometary tail. A light sail is a proposed method of spacecraft propulsion where an ultra-thin reflective sheet catches sunlight, or laser light, and uses radiation pressure for thrust. It's a legitimate concept studied by space agencies and advocated by groups like the Breakthrough Starshot Initiative, which Loeb advises. In principle, an alien civilization might use light sails to send probes across interstellar distances, propelled only by starlight without requiring onboard fuel or engines. The light sail hypothesis was technically possible and mathematically coherent. The physics was sound. An object with the right mass-to-area ratio would indeed experience the observed acceleration from radiation pressure, but most astronomers considered it an unnecessary and implausible explanation. Why invoke alien technology when natural mechanisms involving unusual but not impossible outgassing could explain the data? The principle of Occam's razor suggests that among competing explanations, the one requiring the fewest assumptions is generally preferable. Explaining Oumuamua as a comet with unusual composition or geometry requires assuming conditions different from typical comets, but within known physical possibilities. Explaining it as an alien light sail requires assuming intelligent extraterrestrial civilizations exist, that they build interstellar probes, that such probes are common enough that we'd detect one in our first observation of an interstellar object, and that they happen to look exactly like objects that could be produced naturally. That's a lot of assumptions. Nevertheless, Loeb defended his position vigorously, arguing that scientists should consider all possibilities and not dismiss hypotheses merely because they seem unlikely or uncomfortable. He published a book in 2021 titled Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, laying out his case for Oumuamua being technological. The book became a bestseller, bringing Loeb widespread public attention, but also substantial criticism from many colleagues who felt he was overselling speculation as science. The criticism was multifaceted. Some argued Loeb was violating proper scientific methodology by advocating for a hypothesis without sufficient evidence. Others suggested he was motivated by desire for publicity and media attention, rather than sober scientific analysis. Still others worried that his high-profile speculation about alien technology was feeding conspiracy theories and making legitimate SETI research look less credible by association. But Loeb maintained that science requires openness to unconventional ideas, that the history of science shows experts are sometimes wrong and outsider perspectives sometimes right, and that the potential significance of detecting alien technology justifies treating even low-probability scenarios seriously. He founded the Galileo Project in 2021, a research initiative explicitly dedicated to searching for physical evidence of extraterrestrial technology, including analysis of potential technological signatures in astronomical data and investigation of unidentified aerial phenomena. This was the context when 3I Atlas was discovered in July 2025. Loeb immediately began analysing its properties, looking for features that might suggest something beyond natural origin. Over the following months, he published a series of blog posts on the platform Medium, each one highlighting different aspects of 3I Atlas that he considered unusual or anomalous. These posts were detailed, quantitative, filled with calculations and probability estimates, but they consistently steered toward the possibility, always framed as a possibility, not a certainty, that 3I Atlas might be artificial. When 3I Atlas was discovered in July 2025, Loeb immediately began analysing its properties, looking for anomalies that might suggest technological origin. Over the following months, he published a series of blog posts and papers cataloguing what he considered suspicious features of the interstellar visitor. Some of these observations were based on legitimate astronomical data, others involved statistical arguments about probabilities, and some ventured into more speculative territory. On October 15, 2025, Loeb and two colleagues, Adam Hibbard and Adam Crowell, posted a paper on the AskStiff preprint server titled, "Is the Interstellar Object 3I Atlas Alien Technology?" The paper was explicitly framed as a pedagogical exercise, an exploration of what would be required and what we might expect if 3I Atlas were actually a spacecraft rather than a comet. But despite this framing, the paper's arguments were presented with considerable detail and conviction. The central hypothesis focused on the timing of 3I Atlas's perihelion passage. On October 29, 2025, when the comet reached its closest point to the Sun at about 1.36 astronomical units, Earth was on the opposite side of the Sun. This meant 3I Atlas was in solar conjunction from Earth's perspective, hidden behind the Sun's overwhelming glare and effectively unobservable by ground-based or most space-based telescopes. Loeb argued that this timing was suspiciously convenient if 3I Atlas were a spacecraft wanting to execute a maneuver without being observed. The maneuver in question is called a reverse Oberth maneuver. The Oberth effect, named after physicist Hermann Oberth, describes how rocket propulsion becomes more efficient when performed at high velocities during close approaches to massive bodies. Because kinetic energy scales with the square of velocity, a given thrust applied when you're moving faster produces a larger change in total energy than the same thrust applied when moving slower. Spacecraft designers routinely exploit this effect, timing engine burns to occur at perihelion or during planetary flybys to maximize efficiency. But the effect works in reverse too. If you want to slow down, to reduce your orbital energy enough to be captured by the Sun's gravity, the optimal time to fire braking rockets is at perihelion, when you're moving fastest and deepest in the gravitational well. A relatively modest thrust applied at the right moment could transition a hyperbolic escape trajectory into an elliptical bound orbit. According to Loeb's calculations, if 3I Atlas performed such a maneuver on October 29th while hidden from Earth, it could reduce its velocity enough to become gravitationally bound to the Sun. The resulting orbit might have an aphelion, its farthest point from the Sun, extending far into the outer solar system, perhaps beyond the orbit of Neptune, but it would be elliptical, not hyperbolic. 3I Atlas would return again and again, looping back through the inner solar system every few hundred or thousand years, depending on the specifics of the new orbit. Why would an alien spacecraft want to do this? Loeb suggested several possibilities. If 3I Atlas were a probe sent to explore our solar system, staying in orbit would allow extended observations over many years. It could monitor Earth's radio emissions, track the development of our technological civilization, catalogue the resources available in the solar system, or deploy smaller subprobes to various planets and moons. The hidden perihelion passage would provide perfect cover for the maneuver, ensuring that no telescope on Earth could witness the propulsion system activating or measure the velocity change in real time. The paper went further, exploring darker possibilities. Loeb referenced the dark forest hypothesis, a concept from science fiction author Liu Cixin's novel The Three-Body Problem. The hypothesis proposes that the universe is like a dark forest, where every civilization is a hunter moving silently through the trees, afraid to make noise or show lights, because revealing your position might attract predators. In this framework, interstellar probes might not be peaceful explorers but scouts or weapons sent to identify and potentially eliminate emerging civilizations before they become threats. Could 3i Atlas be such a threat? Loeb calculated that if the object wanted to intercept Earth, the optimal arrival window would be late November to early December 2025. He noted that deploying smaller probes toward Mars, which 3i Atlas passed at close range on October 3rd, would require only modest velocity changes easily achievable with conventional rocket propulsion. The close approaches to Venus, Mars and Jupiter were presented not as coincidences, but as potential evidence of intentional targeting, suggesting a trajectory designed to survey multiple planets in a single pass. The paper acknowledged uncertainties and presented the hypothesis as speculative, noting that the most likely outcome will be that 3i Atlas is a completely natural interstellar object. But it argued that the potential consequences of being wrong, of dismissing a technological visitor as a mere comet, were severe enough to justify serious investigation. If 3i Atlas were indeed artificial and potentially hostile, humanity needed to know before it got closer to Earth. To support his arguments, Loeb proposed a ranking system called the Loeb scale, modelled after the Torino scale used for assessing asteroid impact threats. The scale runs from 0 to 10, with 0 representing an object that's unambiguously natural, and 10 representing definitive artificial technology. Loeb placed 3i Atlas at approximately 4, indicating unusual features warranting investigation, but not conclusive evidence of technology. He argued that any object rating above 5 should trigger coordinated international observation campaigns using all available astronomical resources. The hypothesis generated immediate and intense reactions. Some colleagues praised Loeb for his willingness to think outside conventional frameworks and ask uncomfortable questions. Others accused him of sensationalism, attention-seeking, and damaging the credibility of legitimate scientific research into extraterrestrial life. The debate played out across academic journals, blog posts, social media, and mainstream media outlets, with 3i Atlas becoming a lightning rod for broader tensions about how science should evaluate extraordinary claims. But here's what's crucial to understand. Loeb's hypothesis, however intellectually interesting as a thought experiment, requires 3i Atlas to have actually performed a braking maneuver at perihelion. And now that the comet has re-emerged from behind the Sun and resumed its journey through the solar system, we can test whether that happened. We can measure its velocity, calculate its trajectory, and definitively determine whether 3i Atlas is still on its original hyperbolic escape path or has been captured into orbit around the Sun. And the data is unambiguous. Loeb's case for 3i Atlas potentially being alien technology rests on a series of features he calls anomalies. Let's examine each one carefully, looking at both the claims and the scientific consensus about what these features actually mean. Loeb points out that 3i Atlas's trajectory is aligned to within about 5 degrees of the ecliptic plane, the disc-shaped region where Earth and the other planets orbit the Sun. For an interstellar object arriving from a random direction, the probability of such close alignment is approximately 0.2%, or about 1 in 500. This is presented as evidence that the trajectory might be intentional, designed to facilitate access to the planets. However, astronomers have noted several important caveats. First, observational bias plays a significant role. Our telescope networks are optimized to search for near-Earth objects and asteroids that might pose collision threats. These surveys predominantly scan regions near the ecliptic because that's where most solar system objects are found. An interstellar visitor arriving at a steep angle to the ecliptic might pass through the solar system without being detected at all, especially if it's faint and moving quickly. Second, the 1 in 500 probability sounds impressive, but it's not as extraordinary as it might seem. We've only discovered 3 interstellar objects so far. If we discover 500 interstellar objects over the coming decades, we'd expect one of them to be aligned this closely just by chance. Finding such alignment in the third object we've discovered is lucky, but not impossible. Third, and most importantly, the alignment doesn't actually provide any functional benefit for a spacecraft. If you wanted to visit multiple planets, You wouldn't constrain yourself to the ecliptic plane. You'd use propulsion to adjust your trajectory to reach whichever planets were in favourable positions at the time, regardless of their orbital inclination. The ecliptic alignment might look suspicious to pattern-seeking human minds, but it doesn't serve any obvious purpose that would make it worth the effort for a technological probe. 3i Atlas passed within approximately 28 million kilometres of Mars on October 3rd, about 97 million kilometres from Venus on November 3rd, and will pass about 54 million kilometres from Jupiter in March 2026. Loeb calculates that the combined probability of such close approaches happening by chance is approximately 0.5%, or about 1 in 20,000. But again, observational bias is crucial here. We notice and write papers about interstellar objects that pass near planets because those encounters are scientifically interesting. They provide opportunities for close-range observations from planetary orbiters and might reveal details about the object's composition, structure, and behaviour under different lighting and distance conditions. Objects that don't pass near anything notable are less likely to be studied intensively or make headlines. Moreover, the close approach distances are somewhat misleading. In interplanetary terms, 28 million kilometres to Mars is not particularly close. For comparison, that's about 0.19 astronomical units, roughly 75 times the distance from Earth to the Moon. At that range, gravitational interactions are negligible, and any spacecraft systems would be operating at long-range observation mode, not close encounter mode. If 3i Atlas were actually trying to study Mars, it would want to get much, much closer, perhaps within a few 100,000 kilometres, where high-resolution imaging and atmospheric sampling would be possible. The timing argument is also problematic. Loeb notes that 3i Atlas arrives at each planet's orbital region when the planet happens to be nearby, but this is largely determined by the object's entry point and velocity. Once those parameters are fixed, the close approach distances and times are consequences, not choices. To actually rendezvous with multiple planets would require propulsion to match their orbital velocities, and there's no evidence of such maneuvers. Initial brightness observations suggested 3i Atlas might be quite large, potentially 20 kilometers in diameter if it were a relatively dark asteroid. This would make it unusually massive for an interstellar object, and Loeb argued that finding something so large early in our survey of interstellar visitors was statistically improbable. However, subsequent observations with the Hubble Space Telescope refined the size estimate considerably. By directly imaging the nucleus and measuring the extent of the coma, astronomers determined that the actual diameter is likely between 0.44 and 5.6 kilometers, with a best estimate closer to the lower end of that range. This is still larger than Oumuamua, but not dramatically larger than 2i Borisov, and well within the range of what we might expect for interstellar comets. The confusion arose because 3 Atlas was remarkably bright for its distance when first discovered, leading to the initial large size estimate. But this brightness came from the coma, the cloud of gas and dust surrounding the nucleus, not from the nucleus itself. Active comets can appear much brighter than inert asteroids of the same size because the gas and dust particles scatter sunlight very efficiently. Once astronomers properly accounted for the coma, the size estimate dropped to more reasonable values. Recent calculations based on the lack of significant non-gravitational acceleration suggest 3i Atlas has a minimum mass around 33 billion metric tons. Loeb has argued this implies either a very large nucleus or a hollow structure. But cometary nuclei can be quite dense if they're composed primarily of rock rather than porous ice. A solid rock nucleus, 3 to 4 kilometers in diameter, with typical asteroid-like density, would easily account for the inferred mass while producing the observed level of outgassing. Perhaps the most visually striking feature of 3i Atlas has been its anti-tail, a jet of material pointing toward the sun rather than away from it. Loeb initially presented this as highly unusual, potentially indicative of artificial propulsion, rather than natural outgassing. However, astronomers quickly pointed out that anti-tails are actually well-documented phenomena on comets. They occur when large, heavy dust particles are ejected from the nucleus, but aren't efficiently swept away by solar radiation pressure. These particles follow their own orbital paths, which can appear from Earth's perspective to point in various directions, including sunward. The effect is an optical perspective issue, not a violation of comet physics. Penn State astronomer Jason Wright wrote a detailed rebuttal, citing a 1974 paper about Comet Kohoutek that documented similar sunward-pointing features. He noted that large ejected dust grains don't get swept up by the solar wind on the sun-facing side of a comet, leading to exactly the appearance observed on 3I Atlas. Far from being anomalous, the anti-tail is consistent with normal comet behaviour involving particle-size distributions and dust dynamics. Recent images from November 2025 show 3I Atlas with spectacular jet structures, extending millions of kilometres both toward and away from the Sun. These jets are collimated, meaning they appear as narrow streams rather than diffuse clouds, and they show complex structure with multiple components. Loeb has suggested these might indicate technological thrusters, but similar jet structures have been observed on many active comets as localized patches of ice sublime and vent gas through cracks or weak points in the surface. Observations with the James Webb Space Telescope on August 6th revealed that 3I Atlas has an unusually high ratio of carbon dioxide to water, approximately 8:1. Most comets in our solar system are water-rich, so this composition is distinctive. Additionally, observations detected cyanide at relatively high concentrations, contributing to a vivid green glow observed during the September eclipse. But unusual chemical composition doesn't imply artificial origin. Every comet forms under specific conditions depending on the temperature, pressure, and chemical makeup of its birth environment. 3 Atlas formed in another star system under potentially very different conditions than prevailed in the early solar system. Perhaps the protoplanetary disk where it condensed was particularly carbon-rich, or perhaps it formed in a colder region where carbon dioxide ice was more stable than water ice. Interstellar space itself may have modified the composition. Over millions of years, cosmic radiation can alter the chemistry of surface ices, breaking molecular bonds and creating new compounds. If 3I Atlas spent billions of years drifting through space, its outer layers might have been significantly processed, with the pristine interior only revealed when solar heating removed the irradiated outer shell. The green colour from cyanide is particularly interesting because it appeared suddenly in September, after earlier spectroscopic observations showed relatively low carbon chain content. This has led to speculation about activation or phase changes, but a simpler explanation is that deeper, more volatile rich layers were exposed as surface ice sublimated away. Many comets show evolving colour and composition as they approach the Sun, and different layers of their stratified interiors are revealed. The timing of perihelion, occurring when Earth was on the opposite side of the Sun and unable to observe 3I Atlas, is presented by Loeb as suspiciously convenient for an object wanting to perform an unobserved maneuver. This is perhaps the weakest argument because it involves pure coincidence masquerading as intentional timing. The date of perihelion is determined entirely by when 3I Atlas entered the solar system and its velocity. Those parameters were established potentially millions of years ago when the object was ejected from its home system. There's no way for 3I Atlas to have known, millions of years in advance, where Earth would be on October 29, 2025, relative to the Sun and the comet's trajectory. Moreover, solar conjunction doesn't actually provide perfect cover. Multiple spacecraft, including ESA's Solar Orbiter, NASA's Parker Solar Probe, the SOHO Observatory, and the Stereo satellites, have vantage points different from Earth and could potentially observe objects in solar conjunction. While 3I Atlas was difficult to see from Earth during this period, it wasn't completely invisible to all human observations. If anything, performing a maneuver at perihelion would be suspicious precisely because it's when the object is most thermally stressed and most likely to show natural outbursts of activity. Any non-gravitational acceleration detected at that time could easily be attributed to cometary outgassing rather than propulsion. A spacecraft wanting to make undetected course corrections would be better served waiting until well past perihelion, when it's cooler, less active, and any thrust would stand out more clearly against a quieter background. When examined individually, each supposed anomaly has reasonable natural explanations that don't require invoking artificial technology. When examined collectively, they represent what you'd expect from any interesting astronomical object. A handful of features that are somewhat unusual but not impossible, statistically unlikely but not absurd, surprising but not inexplicable. This is actually how science often works. Nature is diverse and complex, and the universe contains examples of nearly every physically possible configuration. When we discover a new type of object, whether it's a quasar, a magnetar, or an interstellar comet, it almost always shows features that surprise us and challenge our models. That's what makes discovery exciting. But extraordinary claims require extraordinary evidence, and nothing about 3i Atlas rises to the level of extraordinary evidence for artificial technology. The scientific consensus, as expressed by NASA, ESA, and the vast majority of astronomers studying 3i Atlas, is clear. This is a comet from another star system. It's unusual in some respects, as we'd expect given its exotic origin, but it's behaving fundamentally like other comets. It's outgassing normally, producing a coma and tails as solar heating sublimate surface ices. Its trajectory follows gravitational predictions. Its composition, while different from typical solar system comets, is consistent with formation under different stellar conditions. But this leads us to the critical question: what actually happened at perihelion on October 29th? Did 3i Atlas perform a braking maneuver and capture itself into orbit as Loeb hypothesized? Or did it simply pass by the Sun and continue on its hyperbolic escape trajectory, heading back toward interstellar space where it came from? The answer determines not just the fate of 3i Atlas, but the credibility of Loeb's entire hypothesis. As October progressed, and 3i Atlas drew closer to the Sun, it became increasingly difficult to observe from Earth. Its solar elongation, the angular separation between the comet and the Sun in our sky, steadily decreased with each passing day. Understanding solar elongation is crucial for predicting when and where celestial objects can be observed. When an object has a solar elongation of 180 degrees, it's directly opposite the Sun in our sky, rising at sunset, highest at midnight, setting at sunrise. This is optimal viewing geometry. When elongation drops below about 30 degrees, the object is too close to the Sun's position in the sky to be easily observable from the ground, lost in twilight glow or the Sun's overwhelming glare. By early October, 3 Atlas's elongation had dropped to around 40 degrees, meaning the comet was visible only in the evening sky shortly after sunset, low on the western horizon. Observers had perhaps an hour or two of darkness after sunset, before the comet set below the horizon, making observations challenging. The low altitude meant looking through more of Earth's atmosphere, which absorbs and scatters light, reducing contrast and making faint features harder to see. Astronomers call this increased atmospheric path air mass, and high air mass observations are always less than ideal. By mid-October, the elongation had decreased to less than 30 degrees, and 3 Atlas had effectively vanished into the solar glare, invisible to ground-based telescopes. The comet was still there, still moving along its predicted path, but from Earth's perspective it was too close to the Sun to observe safely or productively. Pointing a telescope anywhere near the Sun risks severe damage to both instruments and potentially to observers' eyes, so strict safety protocols prevent observations when objects are within a certain angular distance of the Sun's position. On October 21st, 3 Atlas reached solar conjunction, positioned directly on the opposite side of the Sun from Earth's perspective. For the next several weeks, any attempt to observe it from Earth would require pointing telescopes almost directly at the Sun, an impossible task that would damage instruments and yield no useful data even if attempted. Space-based telescopes like Hubble and Webb, while not limited by daylight, still struggle to observe objects within about 45 degrees of the Sun due to scattered light and thermal constraints. However, a handful of specialized spacecraft were positioned to observe 3i Atlas during this critical period. NASA's Solar and Heliospheric Observatory, SOHO, permanently stationed at the L1 Lagrange point between Earth and Sun, carries coronagraph instruments designed to block the Sun's disk and observe the faint corona and nearby space. The Stereo A spacecraft, orbiting ahead of Earth, had a different viewing angle that might provide glimpses of the comet, and GOES-19, a weather satellite in geostationary orbit, has surprisingly sensitive cameras that can detect faint objects down to magnitude 12. These spacecraft captured images of 3i Atlas between October 18th and 24th, showing a brightening comet with a developing coma and tail. The images revealed something unexpected. 3i Atlas appeared unusually blue in colour, suggesting strong emission from ionized gases, particularly the C2 molecule and possibly ammonia. This bluish tint indicated vigorous outgassing driven by intense solar heating as the comet approached perihelion. Then came the moment of truth. At 11:36 UT on October 29th, 3 Atlas reached perihelion, passing within 1.36 astronomical units of the Sun. That's about 203 million kilometers, or 126 million miles, placing it between the orbits of Earth and Mars. At this distance, solar irradiance reaches approximately 770 watts per square meter, creating intense thermal stress on the comet's surface. Temperature-dependent volatiles that had remained frozen farther out began sublimating rapidly, driving high-speed jets of gas and dust into space. This was the acid test Loeb had written about. If 3I Atlas were a natural comet held together by weak gravitational and mechanical forces, the thermal stress might cause it to fragment into multiple pieces. Comets are notoriously fragile, and many have been observed to break apart during close solar approaches. If 3I Atlas were artificial, with a robust engineered structure, it might remain intact. Alternatively, if it intended to perform a braking maneuver, perihelion would be the optimal time to do so, when the Oberth effect would maximize efficiency. For 2 weeks, astronomers waited as 3 Atlas remained hidden behind the Sun. Orbital mechanics calculations predicted when and where it should emerge, but predictions are one thing and observations are another. Multiple outcomes were possible. The comet might have fragmented into a cloud of debris. It might have brightened dramatically if outgassing intensified, or it might simply continue on its predicted path, unchanged and unremarkable. By early November, 3 Atlas's solar elongation had increased enough for ground-based observations to resume. The comet was now in the pre-dawn sky, rising before the Sun in the eastern horizon. Astronomers around the world trained their telescopes on the predicted position, waiting for confirmation that the comet had survived perihelion and to see what state it was in. Would it still be intact? Would it have fragmented into multiple pieces? Would it have brightened dramatically from increased outgassing, or faded if its volatile ices had been depleted? On November 3rd, multiple observers reported detecting 3 Atlas low in the eastern sky before sunrise. The comet was faint, hovering around magnitude 10 or 11 depending on aperture and observing conditions, requiring telescopes of at least 6 to 8 inches aperture to see clearly but definitely visible to anyone with modest equipment and dark skies, away from light pollution. This brightness was roughly consistent with predictions, perhaps slightly brighter than expected, but not dramatically so. The comet hadn't experienced a major outburst that would have increased its brightness by several magnitudes, nor had it faded significantly. More importantly, initial reports indicated 3 Atlas appeared as a single body, not a dispersed cloud of fragments. This was significant because many astronomers, including Loeb in his pre-perihelion writings, had suggested fragmentation was possible or even likely. Cometary nuclei are thought to be relatively weak mechanically, held together by a combination of self-gravity, which is extremely weak for small bodies, ice cohesion, and in some cases friction between internal components. The thermal stress of perihelion passage, where temperature gradients create differential expansion and contraction stresses, can exceed the structural strength of these weak bodies, causing them to crack and break apart. Comet fragmentation is not uncommon. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces when it passed too close to Jupiter in 1992, and those fragments subsequently crashed into the planet in 1994, creating dramatic impact scars visible even in amateur telescopes. Comet Linear broke up in 2000, Comet Swan fragmented in 2006, and numerous other comets have disintegrated partially or completely when stressed by solar heating or tidal forces. If 3I Atlas were a particularly weak or fragile object, perihelion could have torn it apart. But the early November observations showed no signs of breakup. The comet had a compact concentrated nucleus surrounded by a diffuse coma, exactly what you'd expect from an intact comet. This survival was interpreted in different ways by different researchers. For most astronomers, it simply meant 3I Atlas was structurally robust enough to withstand perihelion heating, probably composed of a mixture of ice and rock with sufficient tensile strength to resist thermal stresses. For Loeb, writing in his blog posts, the survival suggested the object might have greater structural integrity than typical comets, potentially consistent with an engineered structure rather than a loosely bound collection of icy material. Images from the Nordic Optical Telescope on November 11th, captured by astronomers David Jewett and Jane Liu, the same team that discovered the first Kuiper Belt objects in the 1990s and revolutionized our understanding of the outer solar system, provided the clearest post-perihelion views. These images, obtained using the 2.5-meter telescope at La Palma in the Canary Islands, showed 3I Atlas with a prominent coma extending several arc minutes across the sky and multiple jet structures radiating from the nucleus. Most striking was the presence of both a conventional tail, streaming away from the Sun, and the now familiar anti-tail pointing sunward. The conventional tail, created by dust and ionized gas pushed away from the comet by solar radiation pressure and the solar wind, appeared as a faint elongated feature extending, perhaps half a degree across the sky. The anti-tail, composed of heavier dust particles following their own orbital paths, appeared as a bright spike pointing almost directly toward the Sun's position. The nucleus itself appeared compact and singular, with no obvious signs of fragmentation or disruption. The Virtual Telescope project, run by Italian astronomer Gianluca Massi, contributed additional observations from their robotic telescopes in Italy. These images showed the comet's ion tail, the component made of ionized molecules glowing from solar ultraviolet excitation, extending several degrees across the sky. The tail showed complex structure with streamers and knots, typical of cometary ion tails where variations in solar wind density create waves and discontinuities in the plasma. This appearance was entirely consistent with normal cometary behavior and required no exotic explanations. Spectroscopic observations detected strong emission lines from carbon monoxide ions, CO+, created when CO molecules are ionized by solar ultraviolet radiation and then fluoresce, emitting light at specific wavelengths. This bluish emission explained the unusual color noted during perihelion observations from spacecraft. The comet was indeed blue, but not because of any artificial light source. It was blue because its coma was dominated by CO+ emission, which peaks in the blue-green part of the visible spectrum. This chemistry is unusual but not unprecedented. Several comets have shown strong CO+ emission when they're rich in carbon monoxide ice. But the crucial data came from astrometric measurements, precise measurements of 3I Atlas's position in the sky, tracked over multiple nights, and compared to predictions based on gravitational models. Astrometry is one of the oldest branches of astronomy, dating back thousands of years to ancient civilizations tracking planetary positions. Modern astrometry uses digital cameras with known geometric distortions, comparison to reference star catalogues with positions measured by space telescopes like Gaia to sub-millisecond precision, and sophisticated software that can determine an object's position on the sky to extraordinary accuracy. For 3I Atlas, hundreds of astrometric observations were collected from observatories worldwide during the first week of November. Each observation gave a position and time, and when combined with pre-perihelion observations extending back to June, these data points allowed calculation of an updated orbital solution with unprecedented precision. The orbital elements, parameters like eccentricity, perihelion distance, argument of perihelion, and others that fully specify an orbit, could be determined with uncertainties of just a few parts per million. The Minor Planet Center and NASA's Jet Propulsion Laboratory both released updated orbital elements based on observations from October 31st through November 4th. These organizations use slightly different computational methods and data weighting schemes, providing independent verification of results. The data included information from more than 4,000 individual measurements from 227 observatories worldwide, providing an incredibly robust baseline for trajectory analysis. This represents one of the most thoroughly observed interstellar objects in history, with observational coverage spanning nearly 5 months and position measurements from hundreds of different instruments. And the verdict was unambiguous. 3I Atlas is still on a hyperbolic trajectory. Its orbital eccentricity remains greater than 1.0, meaning it retains more than enough velocity to escape the Sun's gravity. No braking maneuver occurred at perihelion. No capture into bound orbit took place. The comet passed by the Sun and is now heading back out toward interstellar space, exactly as predicted by purely gravitational models. There was a small brightening detected, approximately a factor of 5 in the green band centered at 0.464 micrometers wavelength. This is entirely consistent with increased outgassing, as volatile rich subsurface layers were exposed by solar heating. The measured non-gravitational acceleration, the subtle push from outgassing jets, was detected at a level of 3.7 standard deviations, confirming the comet is actively releasing gas as expected for a natural comet at this distance from the Sun. If Thursi Atlas had performed a braking maneuver using rocket engines, as Loeb hypothesized, it would need to expel a significant fraction of its mass as exhaust to achieve the necessary velocity change. The calculations suggest at least 13% of the comet's mass would need to be lost, creating a massive cloud of gas much more extensive than what was observed before perihelion. Future observations, particularly spectroscopic measurements with the James Webb Space Telescope scheduled for December, will provide detailed composition data that can confirm or refute whether such mass loss occurred. But based on current observations, there's no evidence of any maneuver. Thursis I Atlas behaved exactly as a natural comet would behave during perihelion passage. It brightened due to increased outgassing. It maintained structural integrity, remaining a single coherent body. And it continued on its predicted path, following the gravitational trajectory established when it entered the solar system months ago. In other words, 3I Atlas is not staying in our solar system. It's leaving, just as physics predicts it must. The controversy surrounding Avi Loeb's claims about 3I Atlas extends beyond this specific object, touching on fundamental questions about how science evaluates extraordinary claims, how researchers should communicate uncertainty to the public, and what standards of evidence are appropriate when considering the possibility of extraterrestrial technology. Tom Statler, NASA's program scientist for small solar system bodies, has been one of the most vocal critics of the alien spacecraft hypothesis. In interviews and official statements, Statler emphasized that all available data points to 3I Atlas being a natural comet. He noted that the brightness variations, outgassing behavior, and development of tails all match expectations for an icy body being heated by the Sun. It does comet things, Statler told The Guardian. It very, very strongly resembles, in just about every way, the comets that we know. Statler and other NASA scientists have pointed out that comets are inherently unpredictable and often exhibit surprising behavior even when they originate from our own solar system. Comet brightness can vary dramatically as different patches of ice sublime. Jets can erupt unexpectedly from weak points in the surface. Nuclei can fragment or develop unusual tail structures. 3I Atlas, while exhibiting some features that are uncommon, remains within the broad envelope of known cometary behavior. Penn State astronomer Jason Wright took a more detailed approach, systematically addressing each of Loeb's claimed anomalies in a blog post titled Loeb's 3I Atlas Anomalies Explained. Wright acknowledged that Loeb's hypothesis is technically testable, and that considering unusual possibilities can be scientifically valuable. But he argued that none of the features Loeb cites as evidence actually require or even suggest alien technology. For the anti-tail, Wright cited historical observations of similar features on solar system comets, demonstrating this is normal comet physics involving dust particle dynamics. For the collimated jets seen in November images, he noted that many comets show jet structures as localized outgassing creates narrow streams of material. For the unusual composition, he pointed out that interstellar comets formed under different conditions and would naturally have different chemistry. Each supposedly anomalous feature, when examined carefully, has straightforward natural explanations. Chris Lintott from Oxford University was more blunt in his criticism, calling the alien technology hypothesis absolute nonsense and comparing it to seeing lights in the sky and immediately concluding they're flying saucers instead of considering mundane explanations. Lintott argued that Loeb's approach represents bad science, proposing exotic explanations when conventional ones are available and sufficient. The SETI community, researchers dedicated to searching for evidence of extraterrestrial intelligence, has expressed particular frustration. Organizations like the SETI Institute follow rigorous protocols for evaluating potential techno-signatures, requiring multiple independent confirmations and exhaustive elimination of natural explanations before making any claims. They worry that Loeb's high-profile speculation about every unusual astronomical object being potentially alien undermines their credibility and makes their legitimate work harder to fund and defend. Seth Shostak, senior astronomer at the SETI Institute, noted in various interviews that while searching for alien technology is scientifically valid, the standard of evidence must be high. Finding complex radio signals that can't be produced by known natural processes would be compelling evidence. Finding an object that behaves somewhat unusually but remains consistent with natural phenomena is not. However, Loeb has defenders who argue that his approach, while controversial, serves a valuable function. Asking uncomfortable questions and challenging assumptions is part of how science progresses. If researchers never consider unlikely possibilities, they might miss genuinely extraordinary discoveries. The history of science includes numerous examples where consensus views were wrong and maverick thinkers were eventually vindicated. Moreover, some scientists point out that studying interstellar objects for potential technosignatures is becoming increasingly relevant as we discover more such objects. The Vera Rubin Observatory, which began operations in 2025, is expected to detect one interstellar visitor every few months. With potentially dozens or hundreds of these objects discovered over the coming decades, having established protocols for evaluating whether any might be artificial isn't unreasonable. Loeb himself has responded to criticism by emphasizing that he's not claiming certainty, only advocating for thorough investigation. In a November blog post, he wrote, "Let us maintain our childhood curiosity and seek evidence rather than pretend to be the adults in the room that know the answers in advance." He argues that dismissing possibilities without adequate investigation is itself unscientific, and that the potential consequences of missing a genuine technological visitor justify taking the hypothesis seriously enough to gather comprehensive data. The debate has played out in academic journals, on social media, in mainstream media coverage, and at scientific conferences. It's revealed fault lines in the astronomical community about methodology, evidence standards, public communication, and the boundaries between legitimate scientific inquiry and speculation. Some view Loeb as a provocateur making irresponsible claims that feed conspiracy theories. Others see him as a bold thinker, willing to ask questions his colleagues are too timid to address. What's clear is that the controversy has brought unprecedented attention to 3i Atlas and to the broader question of how humanity should prepare for and respond to interstellar visitors. Whether that attention has been beneficial or detrimental to science depends largely on one's perspective about the proper role of speculation in scientific discourse. But here's what's not debatable. As 3i Atlas continues its journey through the solar system, heading toward its closest approach to Earth in December and then outward past Jupiter in March, we'll have months of additional observations to refine our understanding. The data will either support Loeb's claims or refute them, and the nature of science is that data ultimately wins these arguments. Setting aside the controversy about alien technology, 3i Atlas has provided genuine scientific value as only the third confirmed interstellar object ever studied. Every observation contributes to our understanding of how planetary systems form, how material is exchanged between star systems, and what conditions exist in other parts of the galaxy. The scientific harvest from 3i Atlas will be analysed for years to come, appearing in dozens of research papers that incrementally advance our knowledge of these cosmic wanderers. The James Webb Space Telescope's observations on August 6th were particularly revealing. Using the near-infrared spectrograph instrument, Webb measured the composition of gases in 3i Atlas's coma, finding an unusual preponderance of carbon dioxide compared to water. The CO2 to H2O ratio of approximately 8.1 is among the highest ever recorded for any comet, suggesting 3i Atlas formed in a very cold environment where carbon dioxide ice could accumulate preferentially. This extreme ratio tells us something profound about the temperature structure of the protoplanetary disk where 3i Atlas formed. In our solar system, the snow lines for different volatile compounds occur at different distances from the Sun. Water ice condenses at relatively warm temperatures, around 170 Kelvin, which corresponds to distances of about 3 to 5 astronomical units from a Sun-like star. Carbon dioxide has a lower condensation temperature and thus a snow line farther out, perhaps 30 to 40 AU depending on disk conditions. For 3i Atlas to be so enriched in CO2 relative to water suggests it formed beyond the water snowline, but in a region where CO2 was particularly abundant, or it formed in a disk around a star much fainter than our Sun, where temperature gradients were different and the CO2 snowline occurred at closer orbital distances. Alternatively, it might represent material from the very outer reaches of its birth system, where ultraviolet radiation had photodissociated water molecules while leaving CO2 intact. The spectroscopic analysis also revealed trace amounts of carbon monoxide, carbonyl sulfide, and various hydrocarbon molecules. Each of these species provides clues about chemical processes occurring in alien planetary systems. Carbon monoxide is highly volatile and typically sublimes readily, so finding it suggests 3I Atlas has remained cold enough to retain this species throughout its interstellar journey. Carbonyl sulfide forms through sulfur chemistry that depends on the availability of sulfur-bearing species in the original protoplanetary disk. Perhaps most intriguingly, deuterium to hydrogen ratios measured in water vapor from 3I Atlas might eventually tell us about conditions in the molecular cloud that spawned its home star system. Deuterium, the heavy isotope of hydrogen with one proton and one neutron, forms primarily in the Big Bang but gets partially destroyed in stellar interiors. The DH ratio in solar system water is about 150 parts per million. If 3I Atlas shows a significantly different ratio, it might indicate formation from material with a different processing history. The Very Large Telescope in Chile detected hydrogen cyanide, HCN, emission from 3I Atlas in September, with production rates climbing from 1.5 cm25 molecules per second on September 7th to 4.5 cm25 molecules per second by September 14th. This rapid increase coincided with the comet's approach to perihelion and indicates that subsurface layers rich in cyanide-bearing compounds were being exposed as surface ice sublimated away. Cyanide might sound scary, it's certainly toxic to humans, but it's actually a key prebiotic molecule, one of the building blocks potentially involved in the origin of life. HCN can polymerize under the right conditions to form adenine, one of the nucleotide bases in DNA and RNA. It's a precursor to amino acids through Strecker synthesis reactions. Finding abundant cyanide in an interstellar comet demonstrates that complex organic chemistry occurs throughout the galaxy, not just in our solar system. The presence of cyanide also contributed to 3I Atlas's vivid green color observed during September. When HCN is dissociated by solar ultraviolet radiation, it produces diatomic carbon, C2 molecules, which fluoresce strongly in the green part of the spectrum. This green emission is common in comets and has been observed since the 19th century, but seeing it in an interstellar visitor confirms that the same photochemical processes occur regardless of which star system a comet comes from. However, the cyanide detection also raised questions. Earlier spectroscopic observations in July and August had shown relatively low concentrations of carbon chain molecules, suggesting 3 Atlas was depleted in these species compared to typical solar system comets. The dramatic increase in September indicated that the comet's interior is chemically heterogeneous, with different layers having different compositions. This layering might record the comet's formation history, with outer layers forming under different conditions or at different times than inner layers. Spectroscopic observations also detected nickel vapor, an unexpected find that has puzzled researchers studying 3I Atlas and several other recent comets. Nickel emission lines appear in the visible spectrum when metallic nickel is vaporized and excited by sunlight, but the mechanism producing this vapor in cometary coma isn't fully understood. Nickel is a refractory element, meaning it condenses at high temperatures and typically remains locked in solid mineral grains rather than sublimating like ices. For nickel to appear as vapor in a comet's coma, something must be breaking down nickel-bearing minerals or releasing nickel from organic complexes where it's chemically bound. Possible mechanisms include thermal decomposition of organometallic compounds, sublimation of metallic iron nickel grains mixed into the ice, or photodissociation of nickel-bearing molecules by ultraviolet radiation. The detection of nickel in 3I Atlas is scientifically significant because it suggests that whatever process produces nickel emission in solar system comets also operates in interstellar comets. This might indicate that the chemistry of comet formation is relatively universal, occurring similarly in different stellar environments. Or it might suggest that interstellar processing over millions of years creates similar surface chemistry, regardless of initial composition. The Hubble Space Telescope contributed crucial size measurements, constraining the nucleus diameter to between 0.44 and 5.6 kilometers based on observations as of August 20th. This represents a significant refinement from initial estimates that had suggested nuclei up to 20 kilometers across. The smaller size estimate is more consistent with models of interstellar object populations and reduces the statistical improbability that Loeb had highlighted. But size alone doesn't tell the whole story. The nucleus's internal structure, Whether it's a solid chunk of rock and ice, a porous rubble pile of smaller fragments barely held together by weak gravity, or something in between, affects how it responds to thermal stress, how it outgasses, and how long it can survive close approaches to stars. The fact that 3I Atlas survived perihelion intact as a single body suggests some structural integrity. Many comets fragment during close solar approaches when thermal stresses overcome the tensile strength of the material, binding the nucleus together. The survival of 3I Atlas, experiencing heating of about 770 watts per square meter at perihelion distance, indicates either that its nucleus is unusually strong and cohesive, or that it's small enough that thermal gradients don't generate sufficient stress to cause breakup. Photometric observations detecting a rotation period of approximately 16.16 hours with brightness variations suggest the nucleus is non-spherical, probably elongated or irregularly shaped like most small solar system bodies. The rotation rate is consistent with small cometary nuclei, fast enough to be measurable, but not so fast that centrifugal forces would overcome gravity and tear the object apart. The trajectory measurements themselves, compiled from thousands of observations by hundreds of telescopes worldwide, represent an unprecedented dataset for an interstellar object. Previous visitors like Oumuamua were discovered late in their passage and observable for only limited periods. Borisov was better observed but still had observation gaps. 3I Atlas has been tracked from beyond Jupiter's orbit, through perihelion, and will continue to be observable until it moves too far from the Sun in 2026. This extended observation window allows precise measurement of non-gravitational forces. When a comet outgasses, jets of sublimating ice push on the surface, creating subtle accelerations that alter the trajectory in ways gravity alone wouldn't predict. By comparing the comet's position to predictions based purely on gravitational forces from the Sun and planets, astronomers can measure these non-gravitational accelerations with remarkable precision. For 3I Atlas, non-gravitational acceleration was detected at a level of 3.7 standard deviations in post-perihelion observations, confirming the comet is actively releasing gas as expected. The magnitude and direction of this acceleration are consistent with cometary outgassing from a nucleus of its estimated size and activity level. This provides strong confirmation that 3I Atlas is behaving exactly as a natural comet should, following all the physics we understand about how ice sublimates and pushes on surfaces. The precision of these measurements is extraordinary. Modern astrometry can determine the position of bright objects to sub-arc second precision, and with thousands of observations spanning months, velocity changes as small as meters per second become detectable. The consistency between predicted and observed positions for 3I Atlas, accounting for gravitational forces and reasonable cometary outgassing, provides powerful validation of our understanding of orbital mechanics and comet physics. Perhaps the most important scientific legacy of 3I Atlas is what it's taught us about how to study interstellar objects. When Oumuamua was discovered, astronomers were caught off guard. The object was already leaving the inner solar system, moving rapidly outward and fading quickly. By the time the scientific community fully appreciated how unusual it was and coordinated intensive observations, it had become too faint for most telescopes. Many questions about Oumuamua remain unanswered because we simply didn't gather enough data while it was accessible. With 3I Atlas, the astronomical community was better prepared. Observations began immediately upon discovery. Multiple telescopes coordinated campaigns to ensure continuous coverage. Data was shared rapidly through online databases and preprint servers. Spacecraft throughout the solar system were tasked with opportunistic observations. The result is a rich, comprehensive dataset that will support research for years to come. Future interstellar visitors will benefit from this experience. We now know what observations to prioritize: multi-wavelength spectroscopy to characterize composition, high-resolution imaging to measure nucleus size and structure, continuous photometry to detect rotation and outbursts, precise astrometry to measure trajectory and non-gravitational forces. We know to coordinate internationally, share data rapidly, and publish preliminary results quickly while refining analysis as more data accumulates. We've also learned about the importance of space-based assets positioned throughout the solar system. The Mars orbiters that imaged 3I Atlas, the solar observatories that tracked it through perihelion when Earth-based telescopes couldn't, the various heliophysics missions that contributed observations, all demonstrated the value of having diverse observational platforms at different locations. Future missions designed to study transient phenomena could be even more valuable, providing capabilities for rapid response and close-up investigation of interstellar visitors. This is modern astronomy at its finest. Hundreds of researchers coordinating observations, sharing data through online databases, publishing preliminary results to preprint servers where colleagues can access them immediately, rather than waiting months for peer review and journal publication. The pace of discovery has accelerated dramatically in recent decades, enabled by digital communication and communities built around shared scientific interests. The data being collected will fuel research papers for years. PhD dissertations will be written about various aspects of this object, and our models of interstellar matter will be refined and improved. The James Webb Space Telescope's observations on August 6th were particularly revealing and represent some of the highest quality spectroscopic data ever obtained for an interstellar visitor. Webb observed 3I Atlas using the near-infrared spectrograph NUSPEC instrument, which splits infrared light into its component wavelengths with extraordinary precision. Infrared spectroscopy is ideal for studying cometary compositions because many molecules have strong absorption or emission features in the infrared that are weak or absent in visible light. Water, carbon dioxide, carbon monoxide, methane, ammonia, and complex organic molecules all have distinctive infrared signatures. The Webb observations found an unusual preponderance of carbon dioxide compared to water in 3I Atlas's coma. The CO2 to H2O ratio of approximately 8.1 is among the highest ever recorded for any comet, whether from our solar system or interstellar origin. To put this in perspective, typical solar system comets have ratios closer to 110 or 120. Water dominates by large factors. Even comets considered CO2-rich, like Comet 67P Churyumov-Gerasimenko visited by ESA's Rosetta mission, have CO2-H2O ratios around 1.2 at most. This dramatic enrichment in carbon dioxide relative to water tells us something fundamental about 3I Atlas's formation environment. In protoplanetary disks, the relative abundances of different ices depend critically on temperature. Water ice can condense at relatively high temperatures, around 170 Kelvin at typical disk pressures, forming what's called the water snow line. Inside this distance from the young star, temperatures are too high for water ice, so only refractory materials like rock and metal can condense. Beyond the snow line, water ice coats dust grains and allows more rapid planet growth, but CO2 ice requires even lower temperatures to be stable, typically below about 80 Kelvin. In our solar system's formation, this temperature boundary lay somewhere beyond Jupiter's current orbit, in the region where the giant planets formed. Objects that formed closer to the Sun, even if they're beyond the water snow line, tend to be water-rich with only traces of more volatile species. Objects forming much farther out, in the coldest reaches of the disk, can accumulate CO2, CO, methane, and other supervolatile ices. 3I Atlas's composition suggests it formed in a very cold environment, potentially in the outer reaches of its home star's protoplanetary disk, or in a disk around a lower luminosity star where temperatures were colder at all distances. Alternatively, it could represent material from a molecular cloud that was incorporated into a protoplanetary disk without being substantially processed by heating. Some theoretical models suggest that protoplanetary disks inherit material directly from the parent molecular cloud, preserving primordial composition in their outer regions. Another intriguing possibility is that 3I Atlas is genuinely ancient, potentially older than our own solar system. The Milky Way is about 13.6 billion years old, while our solar system formed only 4.6 billion years ago. Stars have been forming planets throughout galactic history, and material ejected from planetary systems billions of years ago is still wandering through interstellar space today. If 3 Atlas formed in an early generation star system, when the galaxy had different chemical composition, specifically different ratios of carbon to oxygen to silicon to other elements, its ice chemistry might reflect those primordial abundances rather than current galactic values. Spectroscopic measurements also revealed the presence of other molecules beyond just CO2 and H2O. Carbon monoxide, CO, was detected at low levels, which is surprising given that CO typically coexists with CO2 in cold ices. Carbonyl sulfide, OCS, was also identified, a sulfur-bearing molecule that provides clues about sulfur chemistry in the comet's formation environment. Sulfur is an important but often overlooked element in planetary chemistry, and measuring sulfur-bearing species in interstellar comets helps us understand whether sulfur abundances and chemical forms vary between different stellar environments. The Very Large Telescope in Chile detected hydrogen cyanide, HCN, emission from 3I Atlas in September, with production rates climbing dramatically as the comet approached perihelion. On September 7th, when the comet was about 2.33 AU from the Sun, the production rate was measured at 1.575 molecules per second. Just 1 week later, on September 14th, the rate had tripled to 4.525 molecules per second, equivalent to about 2 kilograms per second of HCN being released into space. This is scientifically significant for multiple reasons. First, HCN is a key prebiotic molecule, one of the building blocks potentially involved in the origin of life. The Miller-Urey experiments in the 1950s demonstrated that electrical discharges in atmospheres containing methane, ammonia, and water vapor could produce HCN, which then participates in synthesis of amino acids and nucleotide bases, the chemical components of proteins and DNA. Finding HCN in an interstellar comet demonstrates that complex organic chemistry occurs throughout the galaxy, not just in our solar system, and that the raw materials for life are distributed widely through interstellar space. Second, the rapid increase in HCN production as the comet approached the Sun provides information about thermal structure and chemical stratification within the nucleus. HCN sublimates at lower temperatures than water, but higher temperatures than CO2. The fact that HCN emission increased dramatically as the comet moved from 2.3 AU to about 2.0 AU from the Sun suggests there's a temperature-dependent sublimation sequence happening, with different layers being exposed as surface ices ablate away. This kind of compositional evolution is predicted by models of cometary activity, but is rarely observed with such clear resolution. Third, measuring cyanide production rates allows estimation of the comet's size through a technique called mass balance. If you know how much HCN is being produced per second, and you estimate the fraction of the nucleus area that's actively sublimating, typically a few percent, you can work backwards to calculate surface area and hence diameter. The values derived this way are consistent with the size estimates from Hubble imaging, providing independent verification that the nucleus is probably between 1 and 5 kilometers in diameter. The Very Large Telescope observations also detected something unexpected: nickel vapor in the coma. Nickel emission lines at specific wavelengths in the visible spectrum appeared in the spectra, indicating that somehow metallic nickel was being released from the nucleus and vaporized in the coma. This is puzzling because nickel is a refractory element with a very high sublimation temperature, around 3000 Kelvin in vacuum. The coma temperature is maybe a few hundred Kelvin at most, far too cold to sublimate pure nickel metal. This nickel detection mirrors similar findings in several other recent comets, including C2016 R2 Pan-STARRS and C2019 Y4 Atlas, suggesting it might be a more common phenomenon than previously recognized. The mechanism isn't fully understood, but hypotheses include sublimation of organometallic compounds that carry nickel atoms, thermal decomposition of nickel-bearing minerals in fine dust particles lifted by gas drag, or photochemical breakdown of complex molecules in sunlight. Understanding why comets emit metallic vapors has implications for both cometary science and for understanding the distribution of heavy elements in primitive solar system materials. Spectroscopic observations also detected nickel vapor, an unexpected find that has puzzled researchers. Most comets don't show strong nickel emission, but several recent comets, including C2016 R2, Pan-STARRS, and others have exhibited this feature. The mechanism isn't fully understood, but it might involve sublimation of metallic particles mixed into the ice or thermal decomposition of nickel-bearing minerals in the nucleus. The Hubble Space Telescope contributed crucial size measurements, constraining the nucleus diameter to between 0.44 and 5.6 kilometers. This is important because the size, combined with estimates of density and composition, allows calculations of the comet's total mass and internal structure. A small, dense nucleus would imply a predominantly rocky composition, while a larger, fluffier nucleus would suggest porous ice. The trajectory measurements themselves, compiled from thousands of observations by hundreds of telescopes worldwide, represent an unprecedented dataset for an interstellar object. Previous visitors like Oumuamua were discovered late in their passage and observable for only limited periods. Borisov was better, but still observable primarily as it approached the Sun. 3I Atlas has been tracked from beyond Jupiter's orbit through perihelion and will continue to be observable until it moves too far from the Sun in 2026. This extended observation window allows precise measurement of non-gravitational forces. The small accelerations caused by outgassing jets can be detected by comparing the comet's position to predictions based on gravity alone. 3S Atlas shows non-gravitational acceleration consistent with cometary outgassing, with the magnitude and direction matching what's expected for a nucleus of its estimated size and activity level. This is the kind of data that helps validate and refine models of how comets behave. ESA's Mars Express and ExoMars Trace Gas Orbiter captured images of 3I Atlas from Mars orbit on October 3rd, providing a different viewing angle than Earth-based telescopes. While the comet appeared as a faint fuzzy dot in these images, the observations demonstrated the value of having multiple spacecraft positioned throughout the solar system for studying transient events. Future missions, including NASA's Europa Clipper, which passed through 3I Atlas's ion tail in late October, may provide additional data from plasma detectors and other instruments. The colour evolution of 3I Atlas has also been scientifically interesting. The vivid green glow observed during September's total lunar eclipse, which allowed deep imaging under dark skies, suggests strong emission from diatomic carbon, C2 molecules. But earlier spectroscopic observations showed relatively little carbon chain content, implying the composition changed as the comet heated up or as different layers were exposed. This kind of evolution is common in comets but remains poorly understood. Cometary nuclei are thought to be heterogeneous, with different regions having different compositions depending on where and when they formed, and how they've been processed by radiation and thermal cycles. As a comet approaches the Sun and layers sublime away, we essentially see a core sample revealing the comet's formation history. For 3I Atlas, the chemistry suggests a complex history. The high CO2-H2O ratio indicates formation in a cold environment. The cyanide content suggests organic-rich material. The nickel emission hints at refractory mineral content. The temporal evolution demonstrates that cometary nuclei aren't homogeneous snowballs, but layered structures with varying volatile content at different depths. All of this data will be compiled, analysed, and compared to models of cometary formation and evolution. Papers will be written, doctoral theses completed, theories refined. 3I Atlas will take its place in the scientific literature as the third interstellar object, each one teaching us something new about the diversity of small bodies in our galaxy. And when the next interstellar visitor arrives, detected by Vera Rubin Observatory or one of the increasingly capable sky survey systems coming online, we'll be better prepared to study it. We'll know what questions to ask, what measurements to prioritise, what observations need to be made before the object vanishes back into the interstellar void. This is the real legacy of 3I Atlas, not alien conspiracy theories or sensational headlines, but incremental progress in understanding our place in the cosmos. As of mid-November 2025, 3I Atlas has passed its closest approach to the Sun and is now receding, gradually moving higher in the pre-dawn sky as its solar elongation increases. For observers with telescopes, particularly those in the southern hemisphere where the comet appears higher above the horizon, it remains visible as a faint fuzzy patch, moving slowly against the background stars. The comet's trajectory will take it past several more milestones before it finally escapes the Sun's gravitational influence and returns to interstellar space. On November 3rd, it passed within approximately 97 billion kilometers of Venus. While this is too distant for any significant gravitational interaction, or detailed observations from Venus-orbiting spacecraft like Japan's Akatsuki, or NASA's Parker Solar Probe during its Venus flybys, it represents another planetary encounter to note in the books. The most important upcoming event for Earth-based astronomers occurs on December 19, 2025, when 3I Atlas reaches its closest approach to Earth at approximately 1.8 astronomical units, about 269 million kilometers or 167 million miles. This is nearly twice the Earth-Sun distance, so there's absolutely no threat of collision, or even a particularly close pass. But it represents the optimal viewing geometry for ground-based telescopes. At this distance, major observatory facilities, including the Keck telescopes in Hawaii, the European Southern Observatory's Very Large Telescope in Chile, and the Gemini Observatory will be able to obtain high-resolution spectroscopy and imaging. The Hubble Space Telescope has scheduled observations to measure the composition of gas emissions using ultraviolet spectroscopy, which can detect species invisible to ground-based instruments. Most excitingly, the James Webb Space Telescope has observing time allocated for December to obtain detailed infrared spectra of 3I Atlas's coma. Webb's extraordinary sensitivity and spectral resolution should reveal the detailed chemistry of gases being released, potentially identifying complex organic molecules and measuring isotope ratios that provide clues about the comet's age and formation conditions. These December observations are crucial for testing some aspects of Loeb's hypothesis. If 3I Atlas experienced massive mass loss at perihelion, as would be required for the natural explanation of its observed brightening and non-gravitational acceleration, then Webb should detect a greatly expanded and enriched coma containing the vaporized material. If the coma appears similar to pre-perihelion observations without the expected massive gas cloud, it might suggest alternative explanations for the brightening deserve consideration. After passing Earth, 3I Atlas continues outward through the inner solar system. In March 2026, it will pass approximately 54 million kilometers from Jupiter, well beyond the orbits of the Galilean moons but potentially within range of NASA's Juno spacecraft. Juno, which has been orbiting Jupiter since 2016, carries cameras and instruments that could, in principle, observe the distant comet if mission planners choose to allocate resources for the observation. European Space Agency's JUICE spacecraft, currently en route to Jupiter, passed within about 64 million kilometers of 3I Atlas on November 4th, providing post-perihelion observations from its suite of instruments, including visible cameras, infrared spectrometers, and particle detectors. Data from JUICE takes time to downlink due to the spacecraft's distance and limited bandwidth, so analysis of these observations will likely be published in early 2026. As 3I Atlas moves beyond Jupiter's orbit, it will gradually fade from view. Its distance from the Sun increases, reducing solar heating and causing outgassing to diminish. The coma will dissipate, and the nucleus will freeze back into dormancy. By mid-2026, only the largest telescopes will be able to detect it, and by late 2026 or early 2027, it will become effectively unobservable, too faint even for instruments like Hubble or Webb. But the comet continues its journey, completely indifferent to human observations. Over the coming years and decades, it will traverse the outer solar system, passing through the region where Kuiper Belt objects orbit, then entering the scattered disk beyond. Eventually, thousands of years from now, it will pass beyond the heliosphere, the bubble of solar wind that marks the Sun's sphere of influence, and re-enter true interstellar space. From there, 3I Atlas will wander for millions or billions of years through the galaxy, perhaps eventually encountering another star system where, just maybe, inhabitants with telescopes will detect it and wonder about its origins. It's a humbling thought. This visitor to our system might someday visit other systems, carrying in its frozen nucleus a chemical record of multiple stellar environments sampled across vast spans of space and time. For now, though, 3I Atlas belongs to us. We're the civilization that detected it, named it, studied it, and argued about it. When it fades from view next year, we'll have accumulated more data about a single interstellar object than ever before in human history, and when the next one appears, as it inevitably will, we'll be ready. The detection of 3 interstellar objects within just 8 years suggests these cosmic wanderers are far more common than previously believed. Astronomers estimate that at any given time, there are likely several interstellar objects passing through the inner solar system, but most remain undetected because they are too small, too faint, or approaching from directions that our telescope networks don't monitor intensively. This is about to change dramatically. The Vera Rubin Observatory, also known as the Legacy Survey of Space and Time, LSST, achieved first light in 2025 and is now beginning science operations. This revolutionary facility in Chile features an 8.4-meter primary mirror and a 3.2 gigapixel camera, the largest digital camera ever built for astronomy. it will photograph the entire visible sky every few nights, creating an unprecedented real-time map of everything that moves or changes. Rubin's wide field of view and sensitivity will dramatically increase the detection rate for asteroids, comets, and, crucially, interstellar objects. Current estimates suggest Rubin might detect one interstellar visitor per month once fully operational, compared to the handful we've found over the past 8 years. This means we could discover dozens per year, building a statistical sample large enough to characterize the typical properties and diversity of interstellar objects. With more detections comes better science. We'll learn what fraction of interstellar objects are comets versus asteroids. We'll measure the distribution of sizes, compositions, colors, and trajectories. We'll be able to test theories about how planetary systems form and how material is ejected into interstellar space. And yes, we'll be better positioned to evaluate whether any of these objects might be artificial, because we'll have a baseline of normal behavior to compare against. The European Space Agency is preparing for this future with the Comet Interceptor mission, scheduled to launch in 2029. Unlike traditional Comet missions that target specific known objects, Comet Interceptor will park itself at a gravitationally stable point in space and wait. When a suitable target is identified, either a pristine long-period comet from the Oort cloud, or ideally an interstellar visitor, the spacecraft will maneuver to intercept it. Comet Interceptor consists of 3 separate spacecraft, a main probe and 2 smaller modules that will separate before arrival to provide multiple viewing angles. The spacecraft will carry cameras, spectrometers, dust analyzers, and plasma instruments to characterize the comet in unprecedented detail. Unlike flyby missions that spend just a few minutes at closest approach, Comet Interceptor could potentially accompany its target for extended periods, gathering data as activity evolves. The mission's flexible design reflects a crucial lesson learned from Oumuamua. Interstellar objects move fast and are visible for only limited periods. By the time we detect them, design a mission, build a spacecraft, launch, and travel to intercept, they're usually gone. Having spacecraft already in space, waiting for targets of opportunity, is the only practical way to study these objects up close. Michael Kuppers, Comet Interceptor's project scientist, noted in an ESA statement, "When Comet Interceptor was selected in 2019, we only knew of one interstellar object, Oumuamua, discovered in 2017. Since then, 2 more such objects have been discovered, showing large diversity in their appearance. Visiting one could provide a breakthrough in understanding their nature." NASA is also considering missions for rapid response to transient astronomical events. Concepts like the proposed Bridge mission would use advanced propulsion systems to reach distant targets quickly, enabling detailed study of objects that would otherwise escape before traditional missions could arrive. While these remain in early planning stages, the recognition that humanity needs more agile space capabilities is driving innovation in mission design. Beyond dedicated missions, existing spacecraft throughout the solar system provide observation opportunities. The Mars orbiters that imaged 3i Atlas, the Jupiter spacecraft that might observe future visitors, the various heliophysics missions studying the sun and solar wind. All of these can be temporarily repurposed to study interstellar objects when they pass nearby. There's also growing interest in ground-based efforts to characterize interstellar objects. The Breakthrough Listen initiative, funded by the Breakthrough Prize Foundation, uses radio telescopes to search for techno-signatures from extraterrestrial civilizations. As part of their program, they've observed several unusual objects including Oumuamua, looking for any artificial radio signals. They detected nothing, but the precedent has been set. When weird objects show up, it's scientifically valid to check whether they might be technological. Loeb's proposed Galileo project, which aims to search for evidence of extraterrestrial technology through systematic astronomical observations, represents another approach. Whether one agrees with Loeb's specific claims about Oumuamua or 3i Atlas, his broader point has merit. As we discover more interstellar objects, we should have protocols for evaluating their nature that don't automatically assume natural origins, but also don't jump to alien conclusions without extraordinary evidence. The scientific community is gradually developing such protocols. The proposed Loeb scale for ranking interstellar objects by their potential for technological origin is one attempt. Others have suggested modified versions of existing frameworks like the Rio scale for assessing SETI signal candidates. The goal is to have standardized, reproducible methods for evaluating evidence so that future discoveries can be assessed objectively, rather than devolving into the kind of contentious debate that surrounded 3I Atlas. What's certain is that interstellar objects will become increasingly common in astronomical discourse. Each new detection will be compared to previous ones, patterns will emerge, outliers will be identified, and our understanding of these cosmic wanderers will deepen. Some will be boring chunks of rock or ice, indistinguishable from solar system bodies except for their trajectories. Others might be spectacularly unusual, challenging our theories and forcing us to expand our models. And just maybe, though this remains highly speculative and unsupported by current evidence, one might eventually show genuinely anomalous behavior that natural processes can't explain. If that day comes, if we ever do detect an unambiguous techno-signature on an interstellar visitor, the protocols we develop now for evaluating objects like 3I Atlas will prove invaluable. Until then, we watch, we measure, we analyze, and we learn. Let's return to the fundamental question that sparked this entire investigation. Is 3I Atlas staying in our solar system? The answer, based on all available evidence and fundamental physics, is no. 3I Atlas is not staying. It cannot stay without either a massive braking maneuver that would be obvious in observations or a gravitational encounter that the trajectory doesn't support. It is leaving the solar system, and it will never return. Here's why we can say this with confidence. Orbital mechanics is one of the most precisely understood areas of physics. Johannes Kepler worked out the basic laws of planetary motion in the early 1600s. Isaac Newton provided the mathematical framework in the late 1600s. Centuries of astronomical observations have refined and validated these principles to extraordinary precision. We can predict planetary positions years in advance to within kilometers. We can launch spacecraft to distant planets and arrive within minutes of scheduled times. Orbital mechanics works. When 3 Atlas entered the solar system, it brought with it a specific amount of kinetic energy relative to the Sun. This energy, combined with the Sun's gravitational potential, determines its orbital trajectory. The shape of that trajectory, whether elliptical or hyperbolic, depends on whether the total energy is negative or positive. For 3I Atlas, the total energy is definitively positive. This means it's on an escape trajectory, a hyperbolic path. To change that, to transition from escape to capture, requires removing energy from the system. In physics, energy cannot be created or destroyed, only transferred or converted. So where could that excess energy go? There are only a few mechanisms in celestial mechanics that can transfer energy away from an orbiting body. Fire rockets or some other propulsion system to slow down. This requires reaction mass, material to throw in the opposite direction, and energy to accelerate that mass. Newton's third law tells us that for every action there's an equal and opposite reaction. When a rocket expels exhaust at high velocity in one direction, the rocket itself must accelerate in the opposite direction. The amount of velocity change depends on the exhaust velocity and the fraction of the spacecraft's mass expelled as propellant, following the famous Tsiolkovsky rocket equation. For an object as massive as 3I Atlas, estimated at 33 billion metric tons minimum, moving as fast as it is at 68 kilometers per second at perihelion, the energy requirements for significant braking are astronomical. Let's do the math. The kinetic energy of 3I Atlas at perihelion is approximately 12 mv2 g112 through 13 qui 68,000 mes2 7.622 joules. That's 76 zetajoules, or roughly 18,000 megatons of TNT equivalent, more than 1 million times the energy of the largest nuclear weapon ever detonated. To slow 3I Atlas from 68 km to, say, 50 km, a reduction sufficient to transition from hyperbolic to elliptical, you'd need to remove about 30% of its kinetic energy, equivalent to roughly 25 zetajoules or 6,000 megatons. And the exhaust plume from such a burn would be absolutely enormous, orders of magnitude brighter than the natural coma, visible across the entire inner solar system, impossible to mistake for anything other than artificial propulsion. Pass very close to a massive planet and transfer momentum through gravitational interaction in what's called a gravitational slingshot or gravity assist. This is how space missions like Voyager gained enough speed to leave the solar system, and it's how many comets have been captured from hyperbolic to elliptical orbits throughout solar system history. Jupiter is particularly good at this because of its immense mass. 318 times Earth's mass. When a comet passes close to Jupiter, the planet's gravity can add or subtract velocity depending on the geometry of the encounter. If the comet passes in front of Jupiter in its orbit, Jupiter's gravity pulls it forward, speeding it up. If it passes behind, gravity pulls it backwards, slowing it down. The effect scales with the square of the distance. Getting twice as close produces 4 times the velocity change. But here's the crucial point. To get a significant gravitational assist, you need to pass extremely close. Comet Shoemaker-Levy 9, which famously crashed into Jupiter in 1994, was captured into orbit around Jupiter after passing within Jupiter's Roche limit, the distance where tidal forces can tear objects apart. Most gravitational captures require passages within a few planetary radii. 3I, Atlas's closest approach to Jupiter, will be about 54 million kilometers in March 2026. Jupiter's radius is about 70,000 kilometers, so this is roughly 770 Jupiter radii, far too distant for any significant gravitational interaction. At that distance, Jupiter's gravitational effect on 3I Atlas will be utterly negligible, producing velocity changes measured in meters per second at most, not the kilometers per second needed for capture. The same applies to 3I Atlas's encounters with other planets. Its pass by Mars was about 28 million kilometers, and Mars has only about 11% of Earth's mass, making it an even weaker gravitational influencer. Venus is more massive, but 3I Atlas passed at 97 million kilometers. None of these encounters are remotely close enough to produce significant gravitational effects, through a planetary atmosphere and lose velocity through friction. This is how some meteoroids from interplanetary space are captured by Earth, burning up in our atmosphere as they lose kinetic energy to heat, and eventually, if they survive, falling to the surface. Atmospheric drag is extremely efficient at removing energy from moving objects because it creates heat, converting kinetic energy into thermal energy that radiates away. But 3I Atlas isn't passing through anyone's atmosphere. It's moving through the near vacuum of interplanetary space where the density of particles is so low that drag is negligible. Even within the Sun's corona, where plasma density is relatively high by space standards, the drag on a large object like 3I Atlas would be utterly insignificant. You'd need to pass through the dense lower atmosphere of a planet to experience meaningful drag, and 3I Atlas is staying millions of kilometers away from all planetary surfaces. Throw off a large fraction of your mass in a specific direction to create a recoil effect, essentially using your own material as propellant. Comets do this naturally through outgassing, where jets of sublimating ice push on the surface like tiny rocket engines. This produces what astronomers call non-gravitational acceleration, forces that perturb the comet's trajectory beyond what gravity alone would produce. These non-gravitational accelerations are routinely measured on active comets, and they can accumulate over time to produce noticeable changes in position, sometimes amounting to thousands of kilometers of deviation over a comet's orbit. For well-studied periodic comets like Halley's Comet, astronomers must account for these non-gravitational forces to accurately predict when the comet will return. However, the effect is small unless the mass loss is truly enormous. Typical non-gravitational accelerations are measured in units of 10^8 to 10^6 AU per day squared, which translates to tiny fractions of a meter per second squared. The thrust from cometary outgassing is spread over a large surface area and produces acceleration inversely proportional to the comet's mass. For a massive object like 3I Atlas, the outgassing observed so far, about 150 kilograms per second measured by Webb, produces negligible acceleration, less than what can be measured in most astrometric observations. To significantly alter 3I Atlas's velocity through mass ejection would require losing perhaps 10 to 20% of its total mass in a directed manner over a short period. That's billions of tons of material explosively ejected. Such an event would be catastrophic, likely fragmenting the nucleus, and would produce an absolutely massive coma visible even to backyard telescopes. We're not seeing anything remotely like that level of activity interact with other bodies in the solar system through tidal forces or direct impacts. Tidal forces occur when one part of an extended object feels significantly different gravity than another part, and they can transfer energy through internal friction as the object deforms. Collisions can transfer momentum directly, potentially either speeding up or slowing down the colliding bodies, but again, Geometry doesn't support this for 3i Atlas. It's not passing close enough to any body for tidal effects to matter, and the probability of collision in the vast emptiness of interplanetary space is vanishingly small. The solar system is mostly empty space. Collision events are extremely rare on human timescales. None of these mechanisms have occurred in amounts sufficient to capture 3i Atlas. The trajectory calculations based on thousands of precise position measurements from hundreds of observatories worldwide show the comet, following a hyperbolic path that matches gravitational predictions to within measurement uncertainty. There's no missing velocity, no unexplained deceleration, no sign of any capture process. The orbital solution has been refined with each new batch of observations, and it consistently shows eccentricity greater than 1.0, definitively hyperbolic. Could 3i Atlas have performed a braking maneuver at perihelion that we missed because it was hidden behind the Sun? In principle, yes, but several factors argue against this. First, spacecraft don't perform major maneuvers at perihelion when they're thermally stressed and potentially obscured. They perform maneuvers when conditions are optimal for observation and verification. A spacecraft trying to avoid detection wouldn't choose the most obvious time to maneuver. Second, any maneuver large enough to change a hyperbolic trajectory into an elliptical one would require expelling massive amounts of material. That material would still be visible in 3i Atlas's coma, and it would show characteristic chemical signatures different from normal cometary outgassing. Future spectroscopic observations can test for this. Third, and most importantly, if a maneuver occurred, the post-perihelion trajectory would show it. We can calculate what the trajectory should be if 3i Atlas just coasted through perihelion under gravity alone. We can compare that to the observed trajectory. They match. There's no discrepancy requiring a maneuver to explain. Loeb has argued that small, undetected maneuvers might have occurred, too subtle to measure but sufficient to alter the long-term trajectory. But this doesn't hold up to scrutiny. The precision of modern astrometry is extraordinary, down to milliarc seconds for bright objects. Changes in velocity as small as meters per second can be detected over weeks or months of observations. A maneuver large enough to matter would be large enough to see. What about the statistical arguments? The unlikely trajectory alignment, the coincidental perihelion timing, the close approaches to planets. These are interesting coincidences, but that's all they are. Coincidences. Unlikely things happen all the time. The odds of winning the lottery are astronomical, yet someone wins every week. The odds of any specific person existing, considering all the chance events in their ancestors' lives, are infinitesimally small, yet here we all are. When you observe a rare event, you can't then calculate the probability of that specific event and claim it's so unlikely it must be artificial. That's the post hoc reasoning fallacy. You're cherry-picking interesting features after the fact and treating them as if they were predicted in advance. A proper statistical test would require specifying in advance what features would constitute evidence of technology, then checking whether observed objects have those features more often than chance would predict. Loeb's approach of cataloguing surprising things about a specific object and calling them anomalies doesn't meet that standard. Furthermore, selection bias matters. We detect and study interstellar objects that have interesting features. Boring objects that pass through the outer solar system unseen don't make headlines. When every object we study is, by definition, interesting enough to have attracted attention, finding unusual features shouldn't be surprising. The bottom line is this. 3i Atlas is a comet from another star system. It's composed of ice and rock, formed billions of years ago in a protoplanetary disk around a different star. It was ejected into interstellar space by gravitational interactions with giant planets, as happens routinely in planetary system formation. It wandered for potentially millions or billions of years through the galaxy before, by pure chance, entering our solar system. It will pass by the Sun, gathering speed from the Sun's gravity, then slow as it climbs back out of the gravitational well. In a few years, it will cross beyond Neptune's orbit. Decades later, it will reach the heliopause and re-enter interstellar space. Millennia from now, it will be light years away, heading towards some as yet unknown destination in the galactic wilderness. It's not staying. It was never going to stay, and the physics that governs its motion is as certain as any knowledge humanity possesses. The saga of 3i Atlas illustrates several important lessons about science, communication, and how we evaluate extraordinary claims in the age of social media and instant global communication. It's a story that goes beyond just one comet, touching on fundamental questions about how knowledge is created, validated, and communicated to the public. First, there's the lesson about evidence and burden of proof. Carl Sagan famously said, "Extraordinary claims require extraordinary evidence." This principle is foundational to science and represents more than just a catchy phrase. It's a rigorous epistemological framework for evaluating new ideas. When someone proposes that an astronomical object might be alien technology rather than a natural phenomenon, they're making an extraordinary claim. Not impossible, certainly, but extraordinary in the sense that it requires us to accept something we've never confirmed before: that intelligent extraterrestrial civilizations exist, that they build interstellar probes, that such probes are common enough that we detect one in just the third interstellar object ever observed, and that these probes happen to look exactly like objects that could be produced naturally through well-understood astrophysical processes. What constitutes extraordinary evidence? Not just unusual features that natural explanations can account for, even if those natural explanations require some assumptions. Not statistical arguments about low probabilities, especially when those probabilities are calculated after the fact rather than predicted in advance. Extraordinary evidence would be unambiguous techno-signatures, characteristics that cannot plausibly be produced by natural processes and that clearly indicate intelligent design. Examples might include artificial radio signals with complex modulation that conveys information, geometric structures visible in high-resolution images that show obvious engineering like right angles or regular patterns inconsistent with natural fracturing, chemical signatures that require industrial processes to produce and cannot result from natural chemistry, or propulsion systems that clearly violate conservation of momentum as it applies to natural processes like outgassing or radiation pressure. These would be smoking guns, observations that leave no reasonable doubt about artificial origin. 3i Atlas shows none of these unambiguous techno-signatures. Every feature that's been cited as anomalous or unusual has reasonable natural explanations. The trajectory can be explained by ordinary gravitational mechanics, plus normal cometary outgassing effects. The composition can be explained by formation under different stellar conditions than prevailed in our solar system. The visual appearance, including jets, coma, and even the anti-tail, can be explained by normal comet physics involving dust dynamics and perspective effects. The timing of perihelion, while coincidentally convenient for a hypothetical unobserved maneuver, is simply when the object's trajectory brought it closest to the Sun based on when it entered the solar system millions or billions of years ago. Does this definitively prove 3i Atlas is natural? No, because you can never absolutely prove a negative. You cannot definitively prove something is not artificial. There's always the philosophical possibility that sufficiently advanced technology could mimic natural phenomena so perfectly that we couldn't distinguish them. Arthur C. Clarke's famous third law states that any sufficiently advanced technology is indistinguishable from magic, and by extension, sufficiently advanced technology might be indistinguishable from nature. But this is where Occam's razor becomes crucial. Among multiple explanations that all fit the available data, we should prefer the one requiring the fewest assumptions. Explaining 3i Atlas as a comet with somewhat unusual but not impossible composition requires assuming only that comets from other star systems can have different chemistries than ours, a modest and entirely reasonable assumption. Explaining it as alien technology requires assuming intelligent extraterrestrial civilizations exist, that they send probes across interstellar space, that we detected one in just our third observation of an interstellar object despite such objects presumably being rare, and that this probe happens to mimic natural comet behavior in every observable way. That's a much longer chain of assumptions, each adding uncertainty. Second, there's the lesson about how science communicates uncertainty to the public, and how that communication gets distorted through multiple layers of translation. When researchers say something is probably or likely natural, they're expressing appropriate scientific caution, acknowledging that absolute certainty is rarely possible and that small uncertainties always remain. But headlines often drop those qualifiers and present statements as absolute certainties. Scientists confirm comet is natural, rather than scientists conclude comet is most likely natural based on current evidence. Conversely, when someone like Loeb says we should consider the possibility, or keep an open mind about alien technology, headlines often transform that into definitive claims. Harvard professor says comet is alien spacecraft, rather than Harvard professor suggests alien. Spacecraft hypothesis deserves investigation. This distortion happens partly through innocent misunderstanding, science journalists trying to simplify technical discussions for general audiences, and partly through deliberate sensationalism, knowing that provocative headlines generate more clicks, shares, and engagement. The distortion creates real problems. It can make scientists seem closed-minded when they express appropriate skepticism about sensational claims, even when that skepticism is justified by the evidence. It can make legitimate scientific uncertainty look like admission that anything is possible, feeding conspiracy theories. And it can fuel public distrust of science by making the scientific process look arbitrary or politically motivated when different researchers arrive at different conclusions. The media ecosystem, including both traditional journalism and social media, actively rewards sensational content. Algorithms promote posts that generate engagement, which often means controversial, surprising, or fear-inducing material. A headline saying interstellar comet behaves normally and provides valuable scientific data might get a few hundred views. A headline saying Harvard professor, alien probe may be in our solar system goes viral, reaching millions. This creates perverse incentives where researchers might, consciously or not, frame their work in more sensational terms to attract attention, funding, media coverage, or citations. It's not necessarily malicious. Scientists are human and respond to incentives like anyone else. But it contributes to an environment where sober, careful analysis gets drowned out by speculation, presented as serious scientific discourse. The challenge for science communicators, journalists, and scientists themselves is to find ways to make accurate, nuanced scientific stories compelling without resorting to sensationalism or distortion. It's difficult but essential work. Third, there's the lesson about the value and danger of keeping an open mind. Science requires openness to new ideas, willingness to question assumptions, and humility about the limits of our knowledge. These are genuine virtues. Without them, science stagnates into dogma, unable to recognize when paradigms need updating, or when anomalies require new theoretical frameworks. The history of science celebrates researchers who challenge conventional wisdom and turned out to be right. Galileo questioning geocentrism, Wegener proposing continental drift, Alvarez suggesting asteroid impact caused dinosaur extinction. But openness doesn't mean gullibility. Being willing to consider unusual possibilities isn't the same as accepting them without sufficient evidence. The phrase, keep an open mind, sometimes gets weaponized to suggest that skepticism toward extraordinary claims represents narrow-mindedness, when in fact skepticism is the appropriate default position for claims lacking strong evidence. An open mind means being willing to change your view when presented with convincing evidence, not accepting every speculation as equally valid. A truly open mind evaluates claims based on evidence, updates beliefs when new data arrives, and maintains proportional confidence, being very confident about well-established things while remaining provisional about poorly supported things. This balanced approach is harder than either reflexive skepticism or reflexive acceptance, but it's what good science requires. Finally, there's the lesson about preparedness for genuine contact. Loeb is right that humanity lacks coordinated protocols for responding to potential detection of extraterrestrial technology. If we ever do find unambiguous evidence of artificial origin for an interstellar object, we'll need frameworks for verification, international cooperation for follow-up observations, and thoughtful approaches to public communication. The debate about Three-Eye Atlas, however contentious and sometimes frustrating for researchers on all sides, has at least sparked conversations about these topics. It's made more people aware that interstellar objects exist, and that we're entering an era where we'll detect them routinely. It's highlighted the need for better systems for rapid response observations. And yes, it's made some people think about how we'd recognize and respond to genuine alien technology if we ever encountered it. But these benefits have to be weighed against the costs. Confused public understanding, damaged credibility for SETI research, scientists spending time rebutting claims instead of doing research, and the general pollution of information space with speculation presented as legitimate scientific debate. The story of Three-Eye Atlas is ultimately a story about a comet, a fascinating, scientifically valuable, genuinely unusual comet from another star system that has taught us about planetary formation, cometary composition, and the richness of interstellar space. It's provided months of observations that will fuel research papers for years, and it's reminded us that the universe is full of wonders we're only beginning to explore. It's not staying in our solar system, it's leaving as physics demands. But the lessons it's taught us, about science and about ourselves, will remain long after the comet itself has faded from view and returned to the cosmic void from which it came. And when the next interstellar visitor arrives, we'll be watching, measuring, analysing, and yes, debating. Because that's what humans do. We're curious, we wonder, we imagine, and occasionally, very occasionally, we discover something that forces us to reimagine our place in the cosmos. 3i Atlas wasn't that discovery. But someday something might be. If you enjoyed this deep dive into one of 2025's most fascinating astronomical stories, please hit that like button and subscribe to the channel. Let me know in the comments what you think about the controversy surrounding 3i Atlas. Do you think Loeb's hypothesis deserves serious consideration, or is it speculation that distracts from real science? What would it take to convince you that an interstellar object was actually alien technology? The universe is vast, mysterious, and full of wonders we're only beginning to understand. Join me next time as we continue exploring the cosmos, one fascinating story at a time. Until then, keep looking up